Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that challenges everything we think we know about the cosmic dance between fire and ice. I want to take you to a place where shadows hold secrets older than Earth itself, where the closest world to our sun harbours a paradox so beautiful it might just change the way you see the universe. Tonight, we're going to Mercury, that swift messenger of the gods, that scorched wanderer racing through the inner solar system, and we're going to discover something that shouldn't exist but does. Ice, actual water ice, nestled in the eternal darkness of its poles. It's a question that seems impossible at first glance, doesn't it? How could the planet closest to our star, a world where daytime temperatures soar to over 800 degrees Fahrenheit, where lead would melt and flow like water, how could this furnace of a planet cradle frozen water in its polar shadows? It's a question that defies our intuition, that makes us pause and wonder if perhaps we've misunderstood something fundamental about our cosmic neighbourhood. But what if I told you that this apparent contradiction is actually a gentle lesson in the subtleties of planetary physics, a whisper from the universe about how extremes can coexist in ways we never imagined? Before we drift deeper into this mystery together, I'd love to know where you're listening from tonight. Are you tucked into bed in a city where lights compete with stars? Or perhaps you're in a quiet countryside where the Milky Way stretches overhead like a river of dreams. What time is it where you are? Is it that perfect hour when the day's concerns begin to dissolve and the mind opens to wonder? If you're finding comfort in these cosmic contemplations, if these gentle mysteries help you drift toward peaceful sleep, perhaps consider subscribing so we can share more of these nighttime journeys together. There's something beautiful about knowing that somewhere out there, others are pondering the same quiet questions under the same vast sky. You see, Mercury's story is not one of dramatic revelations or shocking discoveries. It's a tale that unfolds slowly, like watching frost form on a winter window, crystal by crystal, pattern by pattern. It's a story that scientists have been piecing together for decades, each observation adding another delicate thread to our understanding. And tonight, we're going to follow those threads together, gently, without hurry, letting the mystery reveal itself at the pace of thought itself. Imagine, if you will, standing on Mercury's surface near one of its poles. The sun, that tremendous sphere of nuclear fire that dominates Earth's sky, would appear about 3 times larger here, a blazing giant that never quite rises above the crater rims that surround you. The sky would be black even in daylight, for Mercury has virtually no atmosphere to scatter light and paint the heavens blue. Stars would shine steadily beside the sun, an impossible sight from Earth but perfectly normal here in this airless realm. And if you were to step into one of those polar craters, into the shadows that the sun's light has never touched, you would find yourself in one of the coldest places in the inner solar system. This is the paradox we're exploring tonight, how the planet nearest to the sun can host some of the solar system's most persistent cold. It's a question that reminds us that the universe rarely follows our simple expectations, that proximity doesn't always mean what we think it means, that shadows can be as powerful as light in shaping the conditions of worlds. As we breathe together in this moment, you and I, we're going to let this mystery wash over us like a cool wave on a warm night, refreshing and surprising, but never overwhelming. The discovery of ice on Mercury wasn't sudden or dramatic. It began with hints, with whispers of data that didn't quite fit the expected pattern. In the early 1990s, astronomers using the massive Arecibo radio telescope in Puerto Rico bounced radar signals off Mercury's surface, and what came back was puzzling. The poles were reflecting those signals in a way that looked remarkably similar to how ice reflects radar waves. But surely that couldn't be right. This was Mercury, after all, the planet named for the swift-footed messenger god, racing around the sun every 88 Earth days, baking in solar radiation that would strip away any volatile substances in moments. Or so we thought. Consider for a moment how we humans love our categories, our neat divisions between hot and cold, between possible and impossible. We see Mercury's proximity to the sun and immediately assume uniform scorching heat. But the universe, in its infinite subtlety, doesn't respect our simple categories. Mercury rotates slowly, so slowly that a single day on Mercury, one sunrise to the next, takes 176 Earth days. That's longer than 2 Mercury years. This strange dance between rotation and revolution creates conditions we never see on Earth, where some places bask in sunlight for months, while others hide in shadow for just as long. And in those shadows, particularly in the deep craters near Mercury's poles, something remarkable happens. Or rather, something remarkable doesn't happen. The sun never shines there. These are what scientists call permanently shadowed regions, places where the geometry of crater walls and the low angle of sunlight at the poles conspire to create eternal night. In these dark sanctuaries, temperatures plummet to -290 degrees Fahrenheit or colder, cold enough not just to preserve ice but to trap it for billions of years. Think about that for a moment. While one part of Mercury endures temperatures that would melt zinc just a few miles away, hidden in shadow, conditions exist that would make Antarctica seem tropical by comparison. It's as if the planet contains within itself two different worlds, two different realities, separated not by distance but by the simple presence or absence of sunlight. This is the kind of cosmic poetry that makes me wonder if the universe has a sense of irony, or perhaps a deep love of paradox. As we settle deeper into this story, let your breathing slow, let your muscles relax. There's no urgency here, no need to grasp or struggle with these ideas. They'll unfold naturally, like flowers opening to moonlight. The ice on Mercury has been waiting there for perhaps billions of years. It can certainly wait for us to understand it at our own pace. Sometimes I think that's one of the beautiful things about studying space. It teaches us patience, shows us that some stories take eons to tell, and that's perfectly fine. The scientific journey to confirm Mercury's ice is itself a meditation on persistence and careful observation. After those initial radar observations from Arecibo, scientists needed more evidence. They needed to see Mercury up close, to measure not just reflections but temperatures, compositions, the actual structure of these polar regions. And so, humanity did what humanity does when faced with a mystery. We sent a messenger to Mercury, a spacecraft named, appropriately enough, Messenger. Messenger, which stood for Mercury Surface, Space Environment, Geochemistry and Ranging, was launched in 2004 and didn't enter orbit around Mercury until 2011. Think about that timeline for a moment. 7 years of travel to reach the innermost planet, 7 years of careful gravitational assists and trajectory adjustments, all to place a school bus-sized robot in orbit around a world that races around the sun faster than any other planet. The patience required, the precision, the faith that the journey would be worth it. These are the qualities that make space exploration a fundamentally hopeful human endeavour. When Messenger finally began its detailed observations of Mercury, it confirmed what the radar had suggested, but in much richer detail. The spacecraft's instruments could peer into those shadowed craters, measure the reflection of neutrons that indicated hydrogen, likely in the form of water ice, and map the temperature variations across the planet's surface with unprecedented precision. What emerged was not just confirmation of ice, but a complex picture of a planet that defies simple description. The ice wasn't just sitting on the surface in most places. Instead, it appeared to be buried beneath a thin layer of dark material, possibly organic compounds delivered by the same comets and asteroids that brought the water. This dark blanket, perhaps only inches thick, acts like an insulating layer, protecting the ice from the few stray photons that might find their way into the shadows and from the heat that conducts through the surrounding rock. It's as if Mercury has tucked its ice beneath a cosmic blanket, keeping it safe and cold through the eons. There's something deeply moving about this arrangement, don't you think? Even on this seemingly hostile world, there are protected spaces, sanctuary zones where water, the substance we associate with life, with flow and change, can rest in perfect stillness. It makes me wonder what other surprises the universe has hidden in plain sight, what other impossibilities are actually just waiting for us to adjust our perspective and see them clearly. As you lie there listening, perhaps you can feel the weight of your own body settling into rest, the way gravity holds you gently to this Earth, just as it holds that ice to Mercury's polar craters. We're all subject to the same fundamental forces, the same laws of physics that govern planets and ice crystals, and the very atoms that make up our bodies. In recognizing this connection, we find our place in the cosmic story, not as outsiders looking in, but as participants in an ongoing dance of matter and energy, heat and cold, light and shadow. The story of how water arrives at Mercury is itself a journey worth contemplating. Picture, if you will, the early solar system, a place of creative chaos where planets were still finding their orbits and countless comets and asteroids crisscrossed space like seeds blown on cosmic winds. Many of these objects contained water ice, formed in the cold outer reaches of the solar system, where water is as common as rock is here in the inner planets. When these icy wanderers crashed into Mercury over billions of years, they delivered their frozen cargo. But not all the water on Mercury necessarily came from outside. Some of it might have formed right there on the planet's surface through a process that sounds almost alchemical. The solar wind, that constant stream of charged particles flowing from the sun, carries hydrogen ions. When these ions strike Mercury's surface, they can combine with oxygen in the rocks to form water molecules. It's a slow process, molecule by molecule, but given billions of years, even slow processes can accumulate significant results. Perhaps there's a lesson there about patience, about how small actions repeated over vast timescales can create something substantial and lasting. The water molecules, however they form or arrive, don't just stay where they land on Mercury. In the heat of the day, any water on the sunlit surface immediately sublimates, transforms directly from ice to vapor without ever becoming liquid. Mercury's lack of atmosphere means there's no air pressure to allow liquid water to exist. These water vapor molecules then begin a journey, bouncing across the planet's surface in great arcing hops, each molecule following its own ballistic trajectory in Mercury's weak gravity. Most of these molecules are lost to space, escaping Mercury's gravitational grip and joining the vast emptiness between planets. But some, by chance or by the subtle influences of Mercury's weak magnetic field, find their way to the poles. And when they encounter those permanently shadowed craters, when they touch those surfaces colder than almost anywhere else in the inner solar system, they stick. They freeze instantly and become part of the ice deposits that have been slowly growing for eons. This process, this gradual migration and accumulation, continues even now as you listen. Right this moment, water molecules are making their way across Mercury's surface, some escaping forever, others finding their final resting place in the polar shadows. It's a kind of molecular poetry, each water molecule on its own journey, contributing to a story billions of years in the making. Sometimes I find myself wondering about the individual histories of those water molecules. Some might have been part of comets that formed in the earliest days of the solar system, witnesses to the birth of planets. Others might have been created just days ago from the marriage of solar wind and Mercury's rocks. All of them now rest together in the darkness, a democratic assembly of hydrogen and oxygen atoms that have found their way to one of the most unlikely refuges in the solar system. The amount of ice we're talking about isn't trivial either. Scientists estimate that Mercury's polar regions could contain anywhere from 100 billion to 1 trillion tons of water ice. That's enough to fill Lake Ontario several times over. Try to imagine that. Lake Ontario's worth of water, frozen and hidden on the planet closest to the sun. If that doesn't make you reconsider what's possible in this universe, I'm not sure what would. But Mercury's ice tells us about more than just Mercury. It's part of a larger story about water in the solar system, about how this precious molecule moves and accumulates and persists, even in the most unlikely places. Our own moon, we've discovered, also harbours ice in its polar shadows. Mars has ice caps and subsurface ice deposits. Even some asteroids carry water ice. What we once thought of as a dry, barren inner solar system turns out to be sprinkled with water in various forms, hidden in shadows and buried beneath dust. This redistribution of water throughout the solar system has profound implications for understanding how planets form and evolve. It suggests that water is more mobile and more resilient than we once believed. It hints that the delivery of water to Earth, the water that fills our oceans and makes life as we know it possible, might have been part of a larger process that affected all the terrestrial planets. We're not separate from this cosmic water cycle. We're part of it, made of it, sustained by it. As you drift deeper into relaxation, perhaps you can sense this connection, this thread of water that links us to Mercury and to the cosmos beyond. The water in your body has its own cosmic history. Some of it might have been in comets, in asteroids, in the primordial cloud that gave birth to our solar system. You are, in a very real sense, made of the same stuff that now rests as ice in Mercury's polar craters. We are all temporary arrangements of ancient atoms, brief patterns in the endless dance of matter and energy. The technology that allowed us to discover and study Mercury's ice is itself a testament to human curiosity and ingenuity. Think about the chain of innovations required: the massive radio telescopes that first detected the unusual radar signatures, the rockets powerful enough to send spacecraft to Mercury, the instruments sensitive enough to detect neutrons and map temperatures from orbit, the computers that process the data and create models of Mercury's surface and interior. Each of these technologies represents thousands of human minds working together, building on generations of knowledge, all to answer questions about a world most of us will never visit. And yet, for all our technology, for all our careful measurements and sophisticated models, Mercury keeps some of its secrets. We still don't know exactly how thick the ice deposits are in some craters. We don't know their precise age or the exact mixture of water ice with other frozen volatiles. We don't fully understand the dark material that covers much of the ice, or how the ice interacts with Mercury's surface over geological time. These unknowns aren't failures. They're invitations to keep exploring, to keep asking questions, to maintain our sense of wonder. This is one of the beautiful aspects of science. It doesn't diminish mystery, but rather deepens it. Every answer we find reveals new questions, like opening doors that lead to rooms full of more doors. The discovery of ice on Mercury doesn't close the book on Mercury's mysteries. It adds new chapters we hadn't even imagined needed to be written, and perhaps that's as it should be. Perhaps a universe that could be fully understood, fully categorized, would be a smaller, less wonderful place. The European Space Agency and the Japan Aerospace Exploration Agency have sent their own messenger to Mercury, Bepi Colombo, launched in 2018 and expected to enter Mercury orbit in 2025. This mission will study Mercury with even more sophisticated instruments, peering deeper into those shadowed craters, analyzing the ice with greater precision, perhaps revealing new aspects of this cosmic paradox we haven't yet imagined. The story of Mercury's ice is still being written, still unfolding, and we're privileged to witness this gradual revelation of cosmic truth. As we continue our gentle exploration, let's take a moment to appreciate the sheer audacity of what we're doing. Here we are, on a small planet orbiting a middle-aged star, using tools we've created from the materials around us to study ice on another world. Ice we'll probably never touch or see with our own eyes, yet we care about it. We spend years of our lives, billions of dollars, incredible effort, all to understand something that has no immediate practical benefit, that won't feed anyone or cure any disease or solve any earthly problem. We do it because we're curious, because we want to know, because understanding our cosmic neighborhood somehow feels important, even if we can't quite articulate why. Maybe that's what makes us human, this drive to understand, to explore, to find ice where ice shouldn't be, and then figure out how it got there and why it stays. Maybe in searching for answers about Mercury's ice, we're really searching for our own place in the cosmos, our own meaning in the vast dance of atoms and energy that surrounds us. And maybe, just maybe, finding ice on the planet closest to the sun tells us that we too can survive and even thrive in unexpected places, that we too can find shelter in the shadows when the light becomes too intense. The polar regions of Mercury, with their eternal shadows and ancient ice, remind me of the quiet places in our own lives, those sheltered spaces where we can rest and restore ourselves, away from the intense light of daily demands. Just as Mercury's ice persists because it found the right conditions, the right protection, perhaps we too need to find or create our own permanently shadowed regions, our own spaces of coolness and calm in a world that often feels too bright, too hot, too demanding. Consider how Mercury's ice has waited billions of years to be discovered, content in its darkness, unchanged by the passage of time that has seen the rise and fall of countless species on Earth, the movement of continents, the birth and death of mountains. There's a profound patience in that persistence, a reminder that not everything needs to happen quickly, that some things are worth the wait, that duration itself can be a form of strength. As we move deeper into our contemplation of Mercury's ice, let's also consider what this discovery means for the possibility of life elsewhere in the universe. Water is essential for life as we know it, and finding water in such an unlikely place as Mercury's poles expands our sense of where water might exist throughout the cosmos. If water can persist on Mercury, what about the moons of Jupiter and Saturn? What about exoplanets orbiting distant stars? What about places we haven't even imagined yet? The ice on Mercury doesn't make Mercury habitable. The conditions are far too extreme, the environment too hostile for any form of life we can imagine. But it does tell us that water, that precious ingredient for life, is more common and more resilient than we once thought. It tells us that the universe might be more accommodating to life than our limited Earth-based perspective once suggested. And that's a thought worth carrying with you into sleep, that the cosmos might be friendlier, more welcoming, more full of possibilities than we ever dared to hope. We're approaching the end of this first part of our journey, but the story of Mercury's ice continues to unfold both in the ongoing scientific investigation and in our own contemplation of its meaning. As you prepare to either drift off to sleep or continue with me into the next phase of our exploration, take a moment to appreciate the strange beauty of this cosmic arrangement. Ice in the shadows of the planet closest to the sun, darkness preserving what light would destroy, cold persisting in the realm of heat. The universe, it seems, loves these kinds of contrasts, these unexpected juxtapositions that challenge our assumptions and expand our understanding. Mercury's ice is just one example of the cosmos's tendency toward complexity, toward arrangements that surprise and delight us. As we continue to explore our solar system and beyond, who knows what other impossibilities we'll discover are actually just realities we hadn't yet learned to see. In the gentle darkness of Mercury's polar craters, ice waits with infinite patience, teaching us that even in the most extreme environments, there are spaces of refuge, zones of possibility, places where the unexpected can not only exist, but persist across cosmic time. Perhaps that's the real message of Mercury's ice, that the universe is full of surprises, full of exceptions to our rules, full of reminders that what we think we know is always less than what there is to discover. As we prepare to delve deeper into the specific mechanisms that allow this ice to exist, into the delicate balance of temperature and pressure, of delivery and loss, of shadow and time, remember that this story is not just about a distant planet and its frozen water. It's about the universe's capacity for paradox, for beauty, for arrangements that shouldn't work but do. It's about our capacity to discover these arrangements, to understand them, to find in them a reflection of our own complex existence. The shadows of Mercury's poles stretch out before us, deep and cold and full of ancient ice, inviting us to continue our exploration, to dive deeper into the mystery, to find in the darkness not fear but wonder, not emptiness but hidden abundance. And so, with the patience of ice that has waited billions of years, we continue our journey into the heart of this cosmic paradox, ready to discover what other secrets Mercury's shadows might hold. Now we turn our attention to the cosmic scale of this phenomenon, to understanding how Mercury fits into the grander story of our solar system's formation and evolution. Because Mercury's ice isn't just a curiosity, a quirk of one small planet. It's a piece of a much larger puzzle, a clue to understanding how worlds form, how water moves through space, and how the conditions for life as we know it came to be. The scale of space and time we're about to explore might seem vast, might make us feel small, but remember, we are the universe becoming aware of itself, and in our understanding, we give meaning to these cosmic processes that would otherwise unfold in unconscious silence. Consider the vastness of time we're dealing with when we talk about Mercury and its ice. The solar system formed about 4.6 billion years ago from a collapsing cloud of gas and dust, a stellar nursery where our sun and all its planets were born. If we compressed those 4.6 billion years into a single day, starting at midnight, the Earth wouldn't form until about 12:10 a.m. Life wouldn't appear until around 5 a.m. Dinosaurs wouldn't show up until about 10:40 p.m. And humans? We'd arrive at 11:59 p.m., just 1 second before midnight. In this compressed timeline, Mercury's polar ice might have started forming in the early morning hours and continued accumulating throughout the entire day, patient and persistent while the rest of the solar system drama unfolded. This temporal perspective helps us understand that Mercury's ice isn't just old, it's phenomenally ancient, possibly dating back to the period scientists call the Late Heavy Bombardment, which occurred roughly 3.8 to 4.1 billion years ago. During this time, the inner solar system was pelted with asteroids and comets in a cosmic shooting gallery, that left its scars on every terrestrial planet and moon. The craters we see on Mercury today, including those polar craters that harbour ice, many of them date from this violent period. But violence, it seems, can create sanctuaries. The very impacts that excavated these craters also created the conditions, the permanent shadows, that would allow ice to persist for billions of years. When we look at Mercury through our telescopes or through the eyes of our spacecraft, we're not just seeing a planet as it is now. We're seeing a world that carries in its surface and in its ice the history of the entire solar system. Every crater tells a story of collision and creation. Every patch of ice represents countless comets and asteroids that met their end on Mercury's surface, delivering their watery cargo to an unlikely repository. We're looking at a museum of solar system history, frozen in time and preserved in shadow. The scale of space surrounding Mercury is equally mind-bending. Mercury orbits the Sun at an average distance of about 36 million miles, though its elliptical orbit takes it as close as 29 million miles and as far as 43 million miles. For comparison, Earth orbits at about 93 million miles from the Sun. This means Mercury receives about 6 times more solar energy per square meter than Earth does. Imagine standing outside on the hottest day you've ever experienced, then multiply that heat by 6. That's the kind of energy Mercury's sunlit surface has to deal with, and yet, just meters away in some cases, in the shadows of crater walls, ice persists in temperatures hundreds of degrees below freezing. The Sun itself, that massive nuclear furnace that dominates Mercury's sky, contains 99.86% of all the mass in our solar system. If the Sun were hollow, you could fit about 1.3 million Earths inside it. And Mercury? It's the smallest planet in our solar system, not much bigger than our moon. You could fit about 18 Mercuries inside Earth. This tiny world, racing around our massive star, somehow maintains these pockets of ice despite being bathed in solar radiation that would seem to make such preservation impossible. But here's where the cosmic perspective becomes even more interesting. Mercury's ability to retain ice in its polar shadows isn't unique in our solar system. It's part of a pattern we're only now beginning to understand. Our moon, as I mentioned earlier, also has ice in its permanently shadowed polar craters. The asteroid Ceres, the largest object in the asteroid belt, has ice in its shadows. Even some craters near the poles of the moon's South Pole Aitken Basin, one of the largest and oldest impact structures in the solar system, harbour ice that might be billions of years old. This pattern tells us something profound about how water behaves in our solar system. It's not just confined to the habitable zone where Earth orbits, that narrow band where liquid water can exist on a planet's surface. Instead, water in various forms exists throughout the solar system, from the ice geysers of Saturn's moon Enceladus to the subsurface ocean of Jupiter's moon Europa, from the polar caps of Mars to the shadows of Mercury. Water, it seems, is everywhere, if you know where and how to look for it. Let's zoom out even further and consider Mercury's place in the architecture of our solar system. Mercury is what astronomers call a terrestrial planet, a rocky world like Venus, Earth, and Mars, as opposed to the gas giants like Jupiter and Saturn, or the ice giants like Uranus and Neptune. But Mercury is an oddball even among the terrestrial planets. Its core, made of iron, takes up about 75% of the planet's radius and about 60% of its mass. For comparison, Earth's core is only about 17% of our planet's mass. It's as if Mercury is mostly a giant ball of iron, with a relatively thin rocky shell around it. This unusual composition tells us something about Mercury's violent past. One theory suggests that Mercury was once a much larger planet, perhaps twice its current size, but a massive collision with another planetary body stripped away much of its rocky mantle, leaving behind the iron-rich world we see today. If this is true, then Mercury is a survivor, a remnant of cosmic violence that reshaped it fundamentally. And yet, despite this catastrophic history, it managed to accumulate and preserve water ice in its polar shadows. There's something poetic about that. A world stripped down to its core, battered by impact, scorched by the sun, yet still harbouring these pristine deposits of ice. The rhythm of Mercury's movement through space is unlike any other planet in our solar system. It rotates on its axis exactly 3 times for every 2 orbits around the Sun, a relationship called a 3.2 spin-orbit resonance. This means that if you could stand on Mercury's surface, you would experience a day, from one sunrise to the next, that lasts 176 Earth days, longer than a Mercury year, which is only 88 Earth days. This bizarre relationship between Mercury's day and year creates extreme temperature variations and unique patterns of sunlight and shadow that contribute to the preservation of polar ice. Imagine the slow progression of sunrise on Mercury. The Sun, appearing about 3 times larger than it does from Earth, would crawl across the black sky so slowly you might not notice its movement without careful observation. At the poles, because of Mercury's minimal axial tilt, just 0.034 degrees compared to Earth's 23.5 degrees, the Sun never rises high in the sky. It skims along the horizon, its light striking the surface at shallow angles, unable to penetrate the deep polar craters where ice hides in eternal darkness. This cosmic choreography, the dance between Mercury's rotation, its revolution around the Sun, and the geometry of its polar craters, creates what scientists call cold traps. These are regions where temperatures remain below about 280 degrees Fahrenheit, cold enough that any water molecule that enters has an extremely low probability of escaping. Over billions of years, these cold traps have accumulated ice like cosmic savings accounts, each deposit of water adding to the principal, compound interest measured in molecules and millennia. The very existence of these cold traps on Mercury challenges our Earth-centric assumptions about planetary environments. We're used to thinking of planets as having relatively uniform conditions, or at least conditions that vary predictably with latitude or season. But Mercury shows us that planets can contain radical extremes, microenvironments that differ from their surroundings by hundreds of degrees, creating unexpected niches where improbable things like polar ice can exist. When we consider the forces at play on Mercury, the intense solar radiation, the extreme temperature swings, the bombardment by the solar wind, the impacts from asteroids and comets, it seems almost miraculous that ice can persist there at all. And yet it does, protected by shadow and insulated by layers of dark material, possibly organic compounds that themselves tell a story of cosmic chemistry and the delivery of life's building blocks throughout the solar system. This brings us to an important realization about our place in the cosmos. We humans, with our narrow range of survivable temperatures, our need for liquid water and breathable air, we might think of ourselves as fragile, as requiring very specific conditions to thrive. But Mercury's ice reminds us that persistence takes many forms. What seems hostile from one perspective might be protective from another. What appears to be a barrier might actually be a shelter. The same crater walls that trap darkness also trap ice. The same lack of atmosphere that allows temperatures to soar also allows them to plummet, creating the very conditions necessary for ice to persist. As we float through this cosmic perspective, feeling perhaps both small and connected to something vast, it's worth remembering that we're not just observers of this cosmic dance, we're participants. The atoms in our bodies, the calcium in our bones, the iron in our blood, the water that makes up most of our mass, these were all forged in the hearts of stars or delivered to Earth by the same kinds of comets and asteroids that brought water to Mercury. We're made of star stuff, as Carl Sagan famously said, but we're also made of comet stuff, asteroid stuff, the same materials that now rest as ice in Mercury's shadows. The discovery and study of Mercury's ice represents humanity at its best, curious, persistent, ingenious. Think about the intellectual journey from ancient astronomers who first identified Mercury as a wandering star, to Galileo who first observed it through a telescope, to the modern scientists who detected its ice through radar observations and spacecraft missions. Each generation built on the knowledge of the previous one, adding their own observations and insights, gradually constructing a more complete picture of this enigmatic world. And we're not done yet. As I mentioned earlier, the Bepi Colombo mission is on its way to Mercury, carrying instruments that will study the ice deposits with unprecedented detail. Future missions might one day land in those shadowed craters, directly sampling the ice, analysing its composition and age, perhaps revealing secrets we haven't even thought to ask about yet. The story of Mercury's ice is still being written, and we're lucky enough to be alive at a time when new chapters are being added regularly. But beyond the scientific importance of Mercury's ice, there's something deeply moving about its mere existence. In a universe that often seems hostile to complexity, to organisation, To anything that fights against the increase of entropy, Mercury's ice represents a kind of cosmic defiance. It shouldn't be there, according to our initial understanding. It should have sublimated away eons ago, lost to space, another casualty of the sun's intense radiation. But it persists, hidden and protected, a testament to the universe's capacity for creating and preserving unlikely things. As you continue to relax, perhaps letting these cosmic scales wash over you like waves on a vast ocean, consider how Mercury's ice connects to the larger story of water in the universe. Water, that simple molecule of 2 hydrogen atoms and 1 oxygen atom, is one of the most abundant compounds in the cosmos. Hydrogen, formed in the first moments after the Big Bang, is the most abundant element in the universe. Oxygen, forged in the nuclear furnaces of massive stars and scattered through space when those stars exploded as supernovae, is the third most abundant element. When these elements come together to form water, they create a substance that seems almost magical in its properties. Water is the only common substance that exists naturally in all 3 states: solid, liquid, and gas. At the temperatures and pressures found on planetary surfaces, its solid form, ice, is less dense than its liquid form, which is why ice floats, a property that has profound implications for life on Earth and potentially elsewhere. Water is also an excellent solvent, able to dissolve and transport a wide variety of substances, making it ideal for the chemistry of life. And water has an unusually high heat capacity, meaning it can absorb and release large amounts of heat without changing temperature much, helping to moderate planetary climates. All of these properties make water crucial for life as we know it, which is why the discovery of water anywhere in the solar system excites astrobiologists. Mercury's ice, while not directly relevant to the search for life, the conditions on Mercury are far too extreme, tells us that water is more widespread and more persistent than we once thought. If water can survive on Mercury, what does that say about its potential presence on exoplanets orbiting other stars? What does it say about the possibility of life elsewhere in the universe? These are the kinds of questions that Mercury's ice raises, questions that extend far beyond the small, swift planet itself. Every scientific discovery, no matter how specific or localized, ripples outward, connecting to other discoveries, other questions, other mysteries. Mercury's ice is a thread in the vast tapestry of cosmic understanding we're constantly weaving, adding to and revising as we learn more about the universe we inhabit. As we near the end of this second chapter of our contemplation, let's return to the human scale for a moment. Tonight, as you lie there listening to this story of ice and shadow, of cosmic time and planetary extremes, you're participating in one of humanity's oldest traditions, wondering about the lights in the sky, trying to understand our place in the cosmos, finding meaning in the dance of celestial bodies. Our ancestors looked up at Mercury, that swift-moving point of light, and saw a messenger god. We look at it now and see a world of extremes that somehow harbours ancient ice, and in that ice we read messages about the history and nature of our solar system. There's continuity in that, a thread connecting us to every human who has ever looked up at the night sky in wonder. We're all part of the same story, the same quest to understand, to find patterns and meaning in the cosmos. Mercury's ice is just the latest chapter in that ongoing narrative, a chapter we're writing together through our collective curiosity and effort. The scale of the cosmos can make us feel small, insignificant, lost in the vastness of space and time. But consider this. We are the only known entities in the universe capable of understanding that vastness, of measuring it, of finding ice on Mercury and knowing what it means. We are the universe becoming conscious of itself, able to appreciate its own beauty and complexity. In that sense, we're not small at all. We're the part of the cosmos that observes, that wonders, that discovers ice where ice shouldn't be, and then figures out how it got there. As we prepare to dive deeper into the specific mechanisms that create and preserve Mercury's polar ice, into the intricate dance of molecules and photons, of temperature and pressure, remember that these details, however technical they might seem, are part of your story too. The water in your body connects you to Mercury's ice, to comets and asteroids, to the vast cycles of matter and energy that have been running since the universe began. You're not separate from this cosmic tale. You're woven into it, made from it, a conscious part of the very fabric of reality we're exploring. The shadows of Mercury's poles stretch out through space and time, reaching all the way to Earth, to this moment, to you lying there in the darkness, contemplating ice on a distant world. In those shadows, in that ice, we find not just water but wonder, not just data but dreams, not just facts, but the profound realization that the universe is far stranger, far more beautiful, far more interconnected than we ever imagined. And now, as we prepare to explore the third chapter of our journey, the actual physical reality of those polar shadows and the ice they protect, take a moment to appreciate the cosmic perspective we've gained. Mercury isn't just a ball of rock and iron racing around the sun, it's a keeper of secrets, a preserver of ice, a testament to the universe's love of paradox and surprise. And we, through our curiosity and ingenuity, have become readers of those secrets, interpreters of that ice, participants in the ongoing revelation of cosmic truth. The art of shadow on Mercury is unlike anything we experience on Earth. Here, shadows are temporary things, moving with the sun's progression across the sky, lasting minutes or hours at most. But on Mercury, in those polar craters, shadows can be eternal, unchanged since the craters were formed billions of years ago. These are shadows with substance, shadows that preserve, shadows that create conditions more extreme than anything in our terrestrial experience. To understand these shadows, we need to think about the geometry of Mercury's poles and the behavior of light in an airless world. On Earth, our atmosphere scatters sunlight, creating the blue sky we see during the day and the twilight that softens the transition between day and night. Even in shadows on Earth, scattered light provides some illumination. We call this diffuse lighting, and it's why you can still see objects even when they're not in direct sunlight. But Mercury has virtually no atmosphere. Its exosphere is so thin that it's essentially a vacuum. Without air to scatter light, shadows on Mercury are absolutely black, as dark as space itself. When sunlight hits the rim of a polar crater at a shallow angle, it cannot penetrate to the crater floor. There's no scattered light to provide secondary illumination, no twilight to soften the transition. The boundary between light and dark is sharp, absolute, a knife-edge division between scorching heat and crushing cold. Imagine standing at the rim of one of these polar craters, with 1 foot in sunlight and 1 in shadow. The foot in sunlight would be exposed to temperatures exceeding 800 degrees Fahrenheit, hot enough to melt lead. The foot in shadow would experience temperatures below minus 280 degrees Fahrenheit, colder than liquid nitrogen. This extreme gradient, existing across a distance of perhaps inches, demonstrates the power of shadow in an airless world. The craters that host Mercury's ice are themselves works of cosmic art, sculpted by impacts over billions of years. Some, like Prokofiev crater near the North Pole, are relatively young in geological terms, perhaps only a few 100 million years old, with sharp, well-defined rims that cast deep shadows. Others are ancient, their rims softened by billions of years of smaller impacts and the slow creep of regolith down their walls. Yet even these older, more degraded craters can maintain permanent shadows if their geometry is right. The key factor is the relationship between the crater's depth, the height of its rim, and its latitude. At Mercury's poles, the sun never rises more than a few degrees above the horizon. For a shadow to be permanent, the crater rim must be high enough relative to the floor that the sun's rays, even at their highest point in Mercury's sky, cannot reach certain areas of the crater floor. It's a delicate balance, a geometric puzzle that nature has solved in dozens of craters across both poles. Scientists have mapped these permanently shadowed regions using sophisticated computer models that account for Mercury's rotation, its orbit around the Sun, and the detailed topography of the polar regions obtained from spacecraft observations. These maps reveal a patchwork of eternal darkness, roughly 50,000 square kilometers of permanently shadowed terrain at the North Pole alone. That's an area about the size of Costa Rica, hidden from the sun's light since the craters were formed. Within these shadows, the quiet geometry of cold creates what we might call a landscape of patience. The ice doesn't flow like glaciers on Earth. It's too cold for that, and Mercury's gravity is too weak. Instead, the ice sits motionless, molecule by molecule, crystal by crystal, a frozen archive of ancient chemistry. The only changes are the slow accumulation of new water molecules that find their way into the shadows, and the even slower loss of molecules that occasionally gain enough energy to escape. the temperature in these permanent shadows isn't uniform. Near the edges, where they border on areas that sometimes see sunlight, temperatures might rise to -200 degrees Fahrenheit. Still incredibly cold, but warm enough that some water molecules can slowly sublimate. Deeper in the shadows, in the most protected regions, temperatures can drop below -350 degrees Fahrenheit, approaching the temperature of space itself. At these temperatures, water ice becomes almost ceramic in its hardness and stability. But water ice isn't the only substance hiding in Mercury's shadows. Spectroscopic observations suggest the presence of other volatile compounds, possibly ammonia, methane, or more complex organic molecules. These substances, even more sensitive to heat than water, can only exist in the very coldest parts of the permanent shadows. They form a kind of chemical gradient, with the most volatile substances in the deepest cold and the more stable compounds, like water ice, extending into slightly warmer regions. The dark material that covers much of the ice adds another layer to this shadow artistry. This material, possibly delivered by the same comets and asteroids that brought the water, or perhaps formed through chemical reactions on Mercury's surface, acts like a protective blanket. It's dark, absorbing what little scattered radiation might find its way into the shadows, but it also insulates the ice beneath from temperature fluctuations and from the few energetic particles that might otherwise cause sublimation. Think of this arrangement as a kind of cosmic terrarium, a self-contained system where the geometry of shadows, the physics of temperature, and the chemistry of ice and organics create a stable configuration that has persisted for eons. It's a natural experiment in preservation, showing us how volatile substances can survive in the most unlikely places if the conditions are just right. The discovery of these shadow sanctuaries required a combination of Earth-based observations and spacecraft missions, each contributing pieces to the puzzle. The story begins in 1991, when astronomers using the Arecibo radio telescope in Puerto Rico decided to bounce radar signals off Mercury's surface. Radar astronomy might seem like an unlikely tool for finding ice, but it turns out that water ice has a very distinctive radar signature. It reflects radio waves in a characteristic way that makes it stand out from rock and dust. When the radar signals came back from Mercury, they showed bright spots at both poles, regions that reflected radio waves just like water ice does. But this was so unexpected, so contrary to what everyone thought they knew about Mercury, that many scientists were skeptical. Could it really be ice, or was it some other substance that happened to have similar radar properties? The debate continued for years, with some scientists proposing alternative explanations like deposits of sulfur or unusually radar-reflective rocks. The confirmation came with NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger carried a suite of instruments that could study the polar regions in multiple ways. Its neutron spectrometer could detect hydrogen, likely in the form of water ice. Its laser altimeter could map the topography of the polar regions in exquisite detail, showing exactly which areas were in permanent shadow. Its cameras, using scattered light from crater walls, could peer into the edges of some shadowed regions. What Messenger found was even more remarkable than the Earth-based radar observations had suggested. Not only was there ice in the permanent shadows, but the distribution of that ice matched perfectly with the temperature models. Where the models predicted it should be cold enough for ice to be stable, ice was found. Where the models suggested it would be too warm, even in permanent shadow, no ice was detected. This correspondence between theory and observation was deeply satisfying, a confirmation that we really do understand the physics at work. Messenger also revealed the layered structure of the polar deposits. In the coldest areas, water ice is exposed at the surface, bright and reflective. In slightly warmer areas, the ice is buried beneath that dark, insulating layer I mentioned earlier. This dark material, which Messenger's instrument suggested might be rich in organic compounds, tells its own story of delivery and preservation. It's as if Mercury's poles are not just freezers but libraries, preserving not just water, but complex carbon-based molecules that might hold clues to the chemical evolution of the solar system. The amount of detail Messenger revealed is staggering. Individual craters could be studied, their ice deposits mapped, their temperatures modelled. Prokofiev crater, which I mentioned earlier, turned out to host one of the largest deposits of water ice, with radar-bright material covering much of its floor. Kandinsky crater, another northern polar crater, shows a complex pattern of ice distribution that reflects the subtle interplay of temperature and topography. Each crater is unique, its ice deposits shaped by its particular geometry and history. As Messenger's mission progressed, the spacecraft's orbit was adjusted to pass closer to Mercury's surface, allowing even more detailed observations of the polar regions. In its final year, Messenger flew as low as 15 kilometers above Mercury's surface, providing images and data of unprecedented resolution. These observations revealed small-scale features in the ice deposits, variations in the dark covering material, and hints of processes we're still trying to understand. One of the most intriguing discoveries was the detection of hollows, small, irregular depressions that appear to be unique to Mercury. These hollows, found across the planet but not in the permanent shadows, suggest that Mercury's surface is still evolving, still losing volatile materials to space. The relationship between these active hollows and the stable ice in the permanent shadows presents an interesting contrast. One part of Mercury is losing volatiles, while another part is preserving them. The European Space Agency's Bepi-Colombo mission, currently en route to Mercury, will add another chapter to this story of shadows and ice. Bepi-Colombo actually consists of two spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, that will study different aspects of the planet. With its advanced instruments, including an improved neutron spectrometer and a thermal infrared imager, Bepi-Colombo will be able to study the ice deposits in even greater detail than Messenger. One of Bepi-Colombo's goals is to determine the thickness of the ice deposits, something Messenger couldn't measure directly. By combining gravity measurements with detailed topographic mapping, scientists hope to estimate how much ice is hiding in those shadows. This will help us understand not just the current state of the ice, but its history, how long it's been accumulating, what the delivery rate might have been, and how it relates to the broader history of water in the inner solar system. Bepi-Colombo will also search for ice in smaller craters and at lower latitudes than previously studied. Climate models suggest that even small shadows, if they're permanent, could host ice. Finding ice in unexpected places would force us to revise our understanding of Mercury's polar environment and might reveal new mechanisms for ice preservation we haven't considered. As we contemplate these shadows and the ice they protect, it's worth reflecting on the nature of permanence itself. We use the term permanently shadowed regions, but permanent is a relative term in the cosmos. These shadows have lasted billions of years, but they won't last forever. The sun is slowly growing brighter as it ages, and in about 1 billion years, it will be luminous enough that some of today's permanent shadows might see sunlight. Impact events could destroy crater rims, allowing light to reach previously shadowed areas. Mercury's orbit could change over geological time, altering the angle at which sunlight strikes the polar regions. Yet for now, for these billions of years that span the history of a life on Earth and more, these shadows have persisted, and the ice within them has waited. There's something profound about that duration, that patience. While Earth's surface has been completely remade multiple times, continents forming and breaking apart, oceans opening and closing, ice ages coming and going, Mercury's polar ice has remained essentially unchanged, a constant in a universe of change. The shadows themselves are like negative spaces in the cosmic canvas, defined not by what they are but by what they're not. Not lit, not warm, not active in the way we usually think of planetary surfaces. Yet these negative spaces are crucial. They're the preservers, the protectors, the quiet guardians of Mercury's most precious deposits. Without them, Mercury would be exactly what we once thought it was. A barren, baked world with no water, no volatiles, no chemical complexity. This interplay between light and shadow, between presence and absence, between the dramatic and the subtle, reminds me of how often the most important things in nature hide in the quiet spaces, the overlooked corners, the shadows both literal and metaphorical. Mercury's ice wasn't discovered by looking at the obvious brightly lit parts of the planet. It was found by peering into the darkness, by being curious about the shadows, by asking what might be hiding where the sun doesn't shine. As you rest there in your own gentle darkness, perhaps preparing for sleep, consider how shadows in your own life might be protective rather than threatening. Just as Mercury's shadows preserve ice that would otherwise be lost, perhaps the quiet, shadowed moments in our lives preserve things that the harsh light of constant activity might destroy: peace, reflection, the slow accumulation of understanding that comes not from dramatic revelation but from patient observation. The physics of Mercury's shadows also teaches us about the importance of boundaries, of transitions, of the spaces between extremes. That sharp line between light and dark on Mercury, with no twilight zone to soften the transition, might seem harsh. But it's precisely this sharpness that creates the conditions for ice to exist. A more gradual transition, a softer boundary, would allow heat to creep into the shadows, destroying the ice. Sometimes it seems preservation requires clear boundaries, definite limits, unambiguous divisions between what is and isn't allowed. Yet within those boundaries, within those sharp-edged shadows, there's remarkable stability. The ice doesn't need to fight to survive. It simply exists in a space where the conditions are right for its existence. There's no struggle, no effort, just the quiet persistence of being in the right place with the right conditions. Perhaps there's a lesson there about finding our own right conditions, our own permanent shadows where we can exist without constant struggle, where preservation doesn't require endless effort, but simply being where we naturally belong. The technology that allows us to study these shadows is itself a kind of light, the light of human curiosity and ingenuity penetrating the darkness of the unknown. Every radar pulse that revealed the ice, every photon collected by Messenger's instruments, every bit of data transmitted across millions of miles of space, represents humanity's effort to illuminate the shadows, to understand what's hidden, to map the unmapped. But even as we shine this light of knowledge into Mercury's shadows, the ice remains in darkness. We can know it's there without disturbing it, can understand it without destroying it. This remote, sensing, this ability to explore without touching, to discover without disturbing, represents a kind of respectful curiosity that perhaps we could apply more broadly. Not everything needs to be brought into the light to be understood. Some things are best appreciated from a distance, known but not possessed, discovered but not disturbed. As we near the end of this contemplation of Mercury's shadows and ice, let's consider what these dark sanctuaries mean for our understanding of the solar system and our place in it. Every planet, every moon, every asteroid might have its own version of Mercury's shadowed craters, places where unexpected things are preserved, where the unlikely becomes possible, where the rules we thought we understood have exceptions we never imagined. These shadows remind us that absence can be as important as presence, that what's not there, heat, light, disturbance, can be as crucial as what is there. They show us that preservation doesn't always require active protection. Sometimes it just requires the right geometry, the right conditions, the right kind of neglect. They demonstrate that even in the most extreme environments, there can be pockets of stability, refuges where delicate things can persist. The ice in Mercury's shadows is like a message from the early solar system, preserved in nature's own time capsule. It tells us about the comets and asteroids that delivered water to the inner planets, about the chemical processes that create and destroy volatile compounds, about the remarkable ability of water to find and persist in the most unlikely places. Each molecule of ice is a tiny historian, carrying information about its origin and journey, waiting in the darkness for us to learn how to read its story. As we prepare to transition to the next phase of our exploration, to dive deeper into the actual mechanisms of ice delivery and preservation, take a moment to appreciate the profound beauty of Mercury's shadowed poles. In a universe that often seems dominated by violent forces, exploding stars, colliding galaxies, searing radiation, here are these quiet, dark spaces where ice rests undisturbed for billions of years. They're like cosmic meditation spaces, zones of stillness in a universe of motion, reminders that not all of nature's power is expressed through action. Sometimes the greatest power is in stillness, in shadow, in the patient preservation of unlikely things. The permanent shadows of Mercury's poles will outlast mountains on Earth, will outlast civilizations, might even outlast our species. Long after the last human has looked up at Mercury in the morning or evening sky, the ice will still be there, waiting in its darkness, keeping its frozen secrets. There's both humility and hope in that thought. Humility in recognizing our brief moment in cosmic time. Hope in knowing that some things endure, that preservation is possible, that even in the harshest environments, sanctuaries exist. And perhaps that's the ultimate message of Mercury's shadowed ice, that the universe, for all its violence and extremes, also has spaces of profound peace, corners of preservation, shadows where unlikely things can not just survive but persist essentially unchanged for cosmic ages. In finding and understanding these spaces, we expand our sense of what's possible, our appreciation for the subtle as well as the dramatic, our recognition that sometimes the most profound discoveries come not from looking at the light but from peering carefully, respectfully, thoughtfully into the darkness. The echoes from Mercury's poles came to us first as whispers of data, anomalies in radar returns that suggested something extraordinary hiding in the darkness. Picture the scene in 1991 at the Arecibo Observatory in Puerto Rico, where the world's largest single-dish radio telescope stretched across a natural valley like a giant ear listening to the cosmos. Scientists there decided to use this massive instrument not just to listen, but to speak, to send powerful radar pulses toward Mercury and wait for the echoes to return, carrying information about the planet's surface that optical telescopes could never reveal. The principle behind radar astronomy is beautifully simple, yet profoundly powerful. Radio waves travel through space at the speed of a light, bounce off planetary surfaces, and return to Earth carrying information about what they struck. Different materials reflect radio waves differently. Rough surfaces scatter them, smooth surfaces reflect them like mirrors, and ice, it turns out, has its own distinctive signature. When those first radar echoes came back from Mercury's poles, they were unexpectedly bright, almost gleaming in the radio spectrum, suggesting surfaces that were remarkably smooth and reflective at radar wavelengths. But science doesn't accept extraordinary claims based on single observations, no matter how compelling. The radar brightness could have been caused by other materials, perhaps deposits of sulfur, or rocks with unusual electrical properties, or some form of metallic condensate we hadn't considered. The scientific community needed more evidence, different types of observations, independent confirmation. And so began a decades-long investigation that would eventually involve some of humanity's most sophisticated instruments, both on Earth and in space. The Arecibo observations were repeated and refined, with scientists using different radar frequencies and polarizations to learn more about the mysterious polar deposits. They found that the radar-bright regions were concentrated in areas that matched where permanent shadows should exist, based on Mercury's topography and the Sun's path across its sky. This correlation was suggestive but not conclusive. After all, our maps of Mercury's polar regions were still relatively crude in the 1990s, based on Earth-based observations and the limited data from Mariner 10's brief flybys in the 1970s. What scientists needed was a dedicated mission to Mercury, a spacecraft that could orbit the planet and study it with multiple instruments over an extended period. That mission was MESSENGER, the Mercury surface, space environment, geochemistry and ranging spacecraft, a name that carried echoes of Mercury's mythological role as the messenger of the gods. Launched in August 2004, MESSENGER would take nearly 7 years to reach Mercury orbit, a journey that required a complex series of gravity assists from Earth, Venus and Mercury itself to slow down enough to be captured by the small planet's weak gravity. Think about the challenge of sending a spacecraft to Mercury. It's not just about covering the distance, it's about matching velocities with a planet that orbits the Sun at an average speed of about 106,000 miles per hour, much faster than Earth's 67,000 miles per hour. A spacecraft launched from Earth starts with Earth's orbital velocity and must somehow shed much of that speed to fall inward toward Mercury. This is why MESSENGER's journey took so long and required such a complex trajectory, looping through the inner solar system like a cosmic pinball, using planetary gravity to adjust its course and speed. When MESSENGER finally entered orbit around Mercury in March 2011, it carried a suite of instruments specifically designed to investigate the polar ice deposits among other scientific objectives. The neutron spectrometer could detect hydrogen, likely in the form of water ice, by measuring how neutrons from cosmic ray impacts were absorbed or scattered by Mercury's surface. The laser altimeter could create detailed topographic maps, showing exactly which areas were in permanent shadow. The gamma-ray spectrometer could identify other elements that might be associated with the ice, and various cameras and spectrometers could study the polar regions in wavelengths, from ultraviolet to near-infrared. The data that flowed back from MESSENGER over its 4-year mission was like a slowly developing photograph, each observation adding detail and clarity to our understanding of Mercury's polar ice. The neutron spectrometer showed clear evidence of hydrogen enrichment in the polar regions, with the highest concentrations exactly where the radar-bright deposits were located. This hydrogen signal extended over thousands of square kilometers, far more extensive than many scientists had expected. But MESSENGER revealed something even more intriguing. The ice wasn't distributed uniformly within the permanently shadowed regions. In the coldest areas, where temperatures never rose above -370 degrees Fahrenheit, water ice appeared to be exposed directly at the surface. These areas showed both the hydrogen signature of water and the high reflectance expected from pure ice. But in slightly warmer areas, and by warmer, I mean places where temperatures might reach -280 degrees Fahrenheit, the ice was buried beneath a layer of dark material about 10 to 30 centimeters thick. This dark material became one of the most fascinating aspects of MESSENGER's discoveries. Spectroscopic analysis suggested it was rich in organic compounds, complex carbon-bearing molecules that might include anything from simple hydrocarbons to more elaborate molecular structures. The layer was dark, darker than most of Mercury's surface, absorbing more than 90% of the light that struck it. Yet paradoxically, this dark blanket was protecting the bright ice beneath, insulating it from temperature fluctuations and from the few photons that might find their way into the shadows through scattered light. MESSENGER's laser altimeter, officially called the Mercury Laser Altimeter or MLA, deserves special attention for its role in confirming the ice deposits. By sending laser pulses to Mercury's surface and measuring the time it took for them to return, MLA could determine the spacecraft's altitude above the surface with an accuracy of about 1 meter. Over millions of measurements, this created a topographic map of Mercury's polar regions with unprecedented detail, revealing the depth and shape of every significant crater, the height of every rim, the subtle undulations of the polar terrain. These topographic maps allowed scientists to model exactly where permanent shadows should exist, based on the sun's maximum elevation at each location. When they compared these shadow maps with the distribution of ice detected by other instruments, the match was nearly perfect. Where the models predicted permanent shadow cold enough for ice, ice was found. Where the models suggested it would be too warm, even in permanent shadow, no ice was detected. This agreement between theory and observation was deeply satisfying, confirming that we truly understood the physical processes at work. MESSENGER also observed the ice deposits at different times of Mercury's day and year, watching for any changes that might indicate active processes. What it found was remarkable stability. The ice deposits showed no detectable changes over the course of the mission, no seasonal variations, no evidence of significant sublimation or deposition. This stability suggested that the ice had reached a kind of equilibrium, with any losses balanced by new arrivals, or perhaps so minimal that they couldn't be detected over the short time span of the mission. One of MESSENGER's most valuable contributions was its ability to observe the same regions with multiple instruments, providing what scientists call multispectral data. For instance, when the spacecraft observed Prokofiev crater, it could measure the hydrogen content with the neutron spectrometer, map the topography with the laser altimeter, analyze the surface composition with the gamma-ray and X-ray spectrometers, and image the crater in multiple wavelengths with its cameras. This multi-pronged approach allowed scientists to build a comprehensive picture of each ice deposit, understanding not just that ice was present, but how much, how pure, how it was distributed, and what other materials were associated with it. The mission also revealed tantalizing hints about the age and origin of the ice deposits. By studying the craters that host ice and comparing them with craters that don't, scientists could begin to piece together a timeline. Some ice-hosting craters were relatively young, their sharp rims and well-preserved features suggesting they formed within the last few 100 million years. Others were ancient, their eroded rims and softened features indicating ages of billions of years. Yet both young and old craters contained ice, suggesting that ice delivery to Mercury has been an ongoing process throughout the planet's history. MESSENGER's observations also extended beyond the ice itself to study Mercury's exosphere, the extremely thin envelope of atoms that surrounds the planet. The spacecraft detected water vapor in the exosphere, particularly over the polar regions, providing direct evidence that some ice was sublimating and contributing water molecules to Mercury's tenuous atmosphere. These water molecules don't last long, they're quickly broken apart by solar radiation or lost to space. But their presence confirmed that the ice deposits are not completely static but part of a dynamic system, albeit one that operates on geological timescales. As Messenger's mission progressed, the spacecraft's orbit was gradually lowered to obtain even more detailed observations. In its final year, the spacecraft flew as low as 15 kilometers above Mercury's surface during each orbit's closest approach. At these low altitudes, Messenger could resolve features just a few meters across, revealing the fine structure of the ice deposits and their covering of dark material. These high-resolution observations showed that the boundary between ice-rich and ice-poor regions could be remarkably sharp, sometimes changing over distances of just tens of meters. The end of Messenger's mission in April 2015 was itself a contribution to science. As the spacecraft ran out of fuel and could no longer maintain its orbit, it was deliberately crashed into Mercury's surface, creating a new crater about 16 meters in diameter. The impact site was carefully chosen to be on the side of Mercury facing Earth at the time, allowing ground-based telescopes to observe the impact and its aftermath. This final act of the mission provided data about Mercury's surface composition and the fate of spacecraft materials in Mercury's extreme environment. But Messenger's legacy extends far beyond its operational lifetime. The data it collected continues to be analysed by scientists around the world, revealing new insights about Mercury's ice and polar regions. Advanced computer modelling, improved analysis techniques, and comparison with data from other missions all contribute to our evolving understanding. Each scientific paper published using Messenger data adds another piece to the puzzle, another thread to the tapestry of knowledge we're weaving about this remarkable planet. The success of Messenger also paved the way for future missions, demonstrating that Mercury could be explored safely and productively, despite the challenges of its proximity to the Sun. The European Space Agency and the Japan Aerospace Exploration Agency took note, accelerating their plans for Bepi-Colombo, a joint mission that would build on Messenger's discoveries with even more advanced instruments. Launched in October 2018, Bepi-Colombo is currently making its way to Mercury, scheduled to enter orbit in December 2025. Bepi-Colombo represents the next chapter in our exploration of Mercury's polar ice. The mission actually consists of two separate orbiters, ESA's Mercury Planetary Orbiter, MPO, and JAXA's Mercury Magnetospheric Orbiter, MMO, that will study different aspects of the planet. MPO carries instruments specifically designed to study the ice deposits in greater detail than Messenger could achieve. Its Mercury Radiometer and Thermal Infrared Spectrometer, MERTIS, will be able to map the temperature of Mercury's surface with high precision, potentially detecting subtle temperature variations within the permanently shadowed regions that could reveal the thermal properties of the ice. Bepi-Colombo's Mercury Imaging X-ray Spectrometer, MIX-S, will use a technique called X-ray fluorescence to determine the elemental composition of Mercury's surface, including the polar regions. When cosmic rays and solar X-rays strike the surface, they cause atoms to emit characteristic X-rays that reveal what elements are present. This could help identify what other materials besides water ice might be present in the polar deposits, adding to our understanding of their composition and origin. The spacecraft also carries an advanced neutron spectrometer called MGNS, Mercury Gamma Ray and Neutron Spectrometer, that will map hydrogen content with even better spatial resolution than Messenger achieved. This improved resolution might reveal ice deposits in smaller craters that Messenger couldn't detect, potentially doubling or tripling our estimate of how much water ice Mercury harbours. It might also reveal variations in ice concentration within individual deposits that could tell us about the history of ice accumulation and loss. One of Bepi-Colombo's most anticipated contributions will be its ability to measure the thickness of the ice deposits. By combining gravity measurements from precise tracking of the spacecraft's orbit with detailed topographic mapping, scientists hope to determine whether the ice forms thin veneers just meters thick or massive deposits that could extend hundreds of meters below the surface. This information is crucial for understanding how much water Mercury has accumulated over its history and what that implies for water delivery to the inner solar system. Bepi-Colombo will also search for ice at lower latitudes than previously studied. While most of Mercury's ice is concentrated near the poles, there might be smaller deposits in shadowed craters at mid-latitudes, or even at the equator if the shadows are deep and permanent enough. Finding ice at lower latitudes would expand our understanding of where volatiles can survive on Mercury, and might reveal additional mechanisms for ice preservation we haven't yet considered. The mission will also study the relationship between Mercury's ice deposits and its magnetic field. Mercury has a weak global magnetic field, about 1% the strength of Earth's, generated by motions in its liquid iron core. This magnetic field creates a magnetosphere that partially shields the planet from the solar wind. Bepi Colombo's magnetometer will map this field in unprecedented detail, potentially revealing whether magnetic effects play any role in directing water molecules toward the poles or protecting the ice deposits from charged particle bombardment. As we await Bepi Colombo's arrival at Mercury, scientists continue to study the planet using Earth-based telescopes that have become increasingly sophisticated since those first radar observations in 1991. The Arecibo telescope, before its unfortunate collapse in 2020, continued to observe Mercury's poles with improved techniques, revealing finer details in the ice distribution. The Goldstone Solar System radar in California and other facilities have taken up this work, using new signal processing methods to extract more information from radar echoes. Ground-based infrared telescopes have also contributed to our understanding of Mercury's ice. By observing Mercury at thermal infrared wavelengths, astronomers can map temperature variations across the planet's surface, including the polar regions. These observations, while not as detailed as spacecraft data, provide a different perspective and can be repeated frequently to look for any changes over time. They've confirmed that the permanently shadowed regions are indeed as cold as models predict, cold enough for ice to be stable over geological timescales. The study of Mercury's ice has also benefited from laboratory experiments here on Earth. Scientists have created Mercury-like conditions in vacuum chambers, subjecting water ice to the temperature extremes and radiation environment it would experience on Mercury. These experiments help us understand how quickly ice sublimates under different conditions, how it interacts with other materials like the dark organic covering, and how it might evolve over billions of years. By comparing laboratory results with observations of actual Mercury ice, scientists can refine their models and better understand the processes at work. Computer simulations have become increasingly important in understanding Mercury's ice deposits. Modern supercomputers can model the movement of individual water molecules across Mercury's surface, tracking their paths from release points to final deposition in polar cold traps. These simulations account for Mercury's gravity, temperature distribution, interaction with the solar wind, and other factors that influence molecular motion. They've shown that water molecules can indeed migrate from equatorial regions to the poles, though the journey might take thousands of hops over days or weeks. Other simulations model the thermal evolution of ice deposits over billions of years, accounting for heat flow from Mercury's interior, changes in the Sun's luminosity, variations in Mercury's orbit, and the insulating effects of covering materials. These models suggest that once ice accumulates to a certain thickness in a permanently shadowed region, it becomes essentially permanent, protected by its own thermal inertia from any temperature fluctuations that might cause sublimation. The discovery and study of Mercury's ice has also inspired new questions and research directions. For instance, if water ice can survive on Mercury, what about other volatile compounds? MESSENGER detected evidence of other frozen volatiles mixed with the water ice, possibly including ammonia, methane, and more complex organic molecules. Understanding the full inventory of Mercury's polar volatiles could tell us much about the chemistry of the early solar system and the delivery of life's building blocks to the inner planets. Scientists are also investigating whether Mercury's ice deposits might preserve a record of the solar system's history. Just as ice cores from Earth's polar regions contain information about past climates and atmospheric composition, Mercury's ice might contain layers that record variations in the rate of water delivery, changes in the solar wind, or even evidence of ancient comet showers. Reading this record would require drilling into the ice, something that would require landing a spacecraft in one of Mercury's permanently shadowed craters, a technological challenge that might not be met for decades. The study of Mercury's ice has implications that extend far beyond Mercury itself. Every airless body in the solar system, from the Moon to asteroids to the moons of the outer planets, might have similar permanently shadowed regions where volatiles can accumulate. Understanding how this process works on Mercury helps us understand where to look for ice elsewhere and what conditions are necessary for its preservation. This knowledge is particularly relevant for future human exploration, as ice deposits could provide water for astronauts, fuel for rockets, and raw materials for construction. The discovery of the ice on Mercury has also influenced our thinking about exoplanets, planets orbiting other stars. Many exoplanets orbit very close to their stars, in positions analogous to Mercury's. If Mercury can retain ice despite its proximity to the Sun, perhaps some of these hot exoplanets might also have volatile deposits in permanently shadowed regions. This possibility expands the range of environments where we might find water and potentially habitable conditions beyond our solar system. As we reflect on these echoes from Mercury's poles, the radar reflections that first revealed the ice, the streams of data from MESSENGER, the anticipated discoveries from Bepi Colombo, we see a story of patient scientific investigation, of technology pushed to its limits, of human curiosity refusing to accept simple answers. Each echo, whether a radar pulse or a spacecraft signal, carries information across the vast emptiness of space, connecting us to this distant world and its hidden ice. The instruments we've built to study Mercury's ice are marvels of human ingenuity. Consider MESSENGER's neutron spectrometer, which could detect the presence of hydrogen by measuring how neutrons created by cosmic ray impacts were absorbed or scattered. This instrument, no larger than a shoebox, could sense the composition of Mercury's surface from hundreds of kilometers away, distinguishing between areas with and without ice based on subtle differences in neutron flux. It's as if we've given ourselves new senses, ways of perceiving reality that go far beyond what evolution equipped us with. Or consider the laser altimeters that map Mercury's topography by timing laser pulses with precision, measured in billionths of a second. These instruments can detect elevation changes of less than a meter from orbit, creating maps so detailed that we can model exactly where shadows fall and where ice can survive. We've become cosmic cartographers, mapping worlds we may never visit in person, but can know intimately through the tools we've created. The radio waves we use for radar astronomy travel to Mercury and back in about 10 to 20 minutes, depending on the planet's positions. Think about that. In less time than it takes to have a coffee break, radio waves can make a round trip to Mercury, bouncing off its icy poles and returning with information about deposits that have been there for billions of years. We're having a conversation with Mercury's ice across hundreds of millions of kilometers, a dialogue mediated by the electromagnetic spectrum and the clever interpretation of reflected signals. This technological reach represents something profound about human nature. We're not content to know only what's immediately around us. We send our robot emissaries to distant worlds, extend our senses across the solar system, and piece together stories about ice on a planet most of us will never see except as a point of light in the sky. This curiosity, this drive to explore and understand, seems to be a fundamental part of who we are as a species. As we near the end of this contemplation of how we've discovered and studied Mercury's ice, it's worth pausing to appreciate the collaborative nature of this endeavour. The discovery involved scientists from many countries, working with instruments built by international teams, sharing data freely, building on each other's work. The radar observations from Puerto Rico were confirmed by a spacecraft built in Maryland, carrying instruments from institutions around the world. Bepi Colombo represents a collaboration between Europe and Japan, with contributions from Russia and other nations. Mercury's ice has become a focal point for international scientific cooperation, a reminder that curiosity about the cosmos transcends national boundaries. The story of these observations also reminds us that discovery is rarely instantaneous. It took decades from the first radar hints to the detailed confirmation by MESSENGER. It will take more years for Bepi Colombo to add its contributions. Science often moves at this deliberate pace, each observation building on the last, each mission learning from its predecessors. There's a patience to this process that mirrors the patience of the ice itself, waiting in Mercury's shadows for billions of years to be discovered. And what of future observations? Even as Bepi Colombo makes its way to Mercury, scientists are planning the next generation of missions and instruments. Concepts for Mercury landers that could directly sample the ice are being studied. New radar techniques that could penetrate deeper into the deposits are being developed. Advanced telescopes, both on Earth and in space, might soon be able to study Mercury's ice in wavelengths, and with resolutions we can barely imagine today. Perhaps one day, human explorers will stand at the rim of a polar crater on Mercury, looking down into shadows that have persisted since before life emerged on Earth. They'll see with their own eyes what we now know only through the whispered data of our instruments. Ice that shouldn't exist but does. Water in the last place anyone would expect to find it. Until that day, if it ever comes, we'll continue to listen to the echoes from Mercury's poles, each observation adding another note to the cosmic symphony of discovery. The physics of stillness on Mercury operates according to rules that would seem alien to us here on Earth, where water flows, evaporates, and precipitates in an endless cycle driven by heat and gravity. On Mercury, in those perpetually shadowed craters, water ice exists in a state of such profound stillness that individual molecules might remain in place for millions of years, locked in crystal lattices that barely vibrate even at the atomic level. This is preservation through physics, through the fundamental laws that govern how matter and energy interact in extreme conditions. To understand this stillness, we need to first understand what scientists call cold traps, regions where temperatures are so low that volatile molecules, once they arrive, cannot escape. The concept is elegantly simple. When a water molecule in vapor form encounters a surface cold, enough, it loses its kinetic energy and sticks, becoming part of the ice deposit. To escape, that molecule would need to gain enough energy to break free from the ice crystal structure and achieve escape velocity. But in Mercury's polar cold traps, where temperatures can drop below -370 degrees Fahrenheit, the probability of a molecule gaining that much energy is essentially zero. The mathematics of molecular motion at these temperatures is fascinating. Temperature is really just a measure of average molecular kinetic energy, how fast molecules are moving or vibrating. At room temperature on Earth, water molecules in the air zip around at speeds of about 600 meters per second. But temperature follows a distribution. Some molecules move faster, some slower. At any given moment, a tiny fraction of molecules in liquid water have enough energy to escape as vapor, which is why puddles evaporate even at temperatures well below boiling. But as temperature drops, this distribution shifts dramatically. At -370 degrees Fahrenheit, the average water molecule in ice vibrates so slowly that it would take longer than the age of the universe for it to spontaneously gain enough energy to escape. The ice becomes, for all practical purposes, permanent. It's not that sublimation stops entirely. Quantum mechanics tells us there's always some infinitesimally small probability of escape, but the rate becomes so slow that it's effectively zero on any timescale we can comprehend. This extreme cold does more than just trap water molecules. It fundamentally changes the properties of ice itself. At Earth temperatures, ice is relatively soft and can flow like a very slow liquid, which is how glaciers move. But at Mercury's polar temperatures, ice becomes harder than rock, more like a ceramic material than the ice we're familiar with. It doesn't flow, doesn't deform, doesn't do anything except sit there, molecule by molecule in perfect crystalline stillness. The regolith, the layer of dust and broken rock that covers much of Mercury's surface, plays a crucial role in this physics of preservation. In many of Mercury's shadowed craters, the ice isn't exposed at the surface, but buried beneath a layer of this regolith, possibly mixed with dark organic materials. This covering acts as both an insulator and a barrier, performing multiple functions that help preserve the ice beneath. First, the regolith provides thermal insulation. Even though the permanently shadowed regions never receive direct sunlight, they do experience some heating from the surrounding sunlit terrain through thermal radiation and heat conduction through the ground. The regolith layer, with its low thermal conductivity, slows this heat transfer to a crawl. Heat that might otherwise reach the ice and cause sublimation is absorbed and dissipated in the regolith layer, never penetrating deep enough to affect the ice. Second, the regolith acts as a physical barrier to sublimation. Even if a water molecule at the ice surface gains enough energy to break free, it must then navigate through the porous regolith layer to escape to space. This journey through the regolith is like a three-dimensional maze at the molecular level. The molecule might bounce off dust grains hundreds or thousands of times, losing energy with each collision, before either escaping or more likely being recaptured by the ice below. The dark material mixed with the regolith adds another layer of protection. This material, possibly rich in organic compounds, is extremely dark, darker than asphalt or charcoal. It absorbs more than 90% of any light that strikes it, which might seem counterproductive for keeping things cold. But in the permanently shadowed regions, there's essentially no light to absorb. Instead, this dark material acts as an effective radiator of thermal energy, helping to keep the underlying ice cold by efficiently radiating away any heat that does reach it. The pace of sublimation from Mercury's ice deposits is so slow that it challenges our ability to measure or even calculate. Scientists estimate that in the coldest parts of the permanently shadowed regions, the sublimation rate might be less than 1 millimeter per billion years. To put that in perspective, if you started with an ice cube 1 meter thick at the formation of the solar system, you'd still have more than 99.9% of it today. This is preservation on a cosmic scale, a demonstration of how the right conditions can essentially stop time for volatile materials. But the physics of Mercury's ice involves more than just cold temperatures and low sublimation rates. There's also the question of how water molecules behave when they do occasionally escape from the ice. In Earth's atmosphere, water vapor can travel as a gas carried by winds and convection. But Mercury has no atmosphere to speak of. Its exosphere is so thin that molecules travel in ballistic trajectories, like tiny projectiles following parabolic paths determined by Mercury's gravity and their initial velocity. When a water molecule does manage to escape from Mercury's ice, it begins what scientists call a random walk across the planet's surface. The molecule flies in an arc until it strikes the surface again, where it might stick temporarily if the surface is cold enough, or immediately bounce off if it's warm. This process, called thermal hopping, can carry a molecule thousands of kilometers across Mercury's surface through hundreds or thousands of individual hops. The fate of these hopping molecules depends on several factors. If they hop into sunlight during Mercury's day, they'll likely be photodissociated, broken apart by ultraviolet radiation from the sun into hydrogen and oxygen atoms. The lightweight hydrogen usually escapes to space, while the heavier oxygen might remain and potentially recombine with other hydrogen to form water again. If the molecule hops at night, it might survive longer, potentially making its way to another cold trap where it can be recaptured. This molecular migration creates what scientists call a water cycle on Mercury, though it's unlike any water cycle on Earth. There's no precipitation, no flowing water, no clouds. Instead, individual molecules make solo journeys across the planet, some escaping to space, others finding their way to the polar cold traps. It's a cycle that operates molecule by molecule, hop by hop, over timescales that dwarf human experience. The efficiency of Mercury's cold traps is remarkable. Models suggest that once a water molecule enters a permanently shadowed region cold enough to trap it, the probability of that molecule eventually escaping back to space is less than 1 in a million. This efficiency means that even a very small rate of water delivery to Mercury, from micrometeorite impact solar wind interactions, or the occasional comet, can lead to significant accumulation over billions of years. The solar wind plays a complex role in this physics of preservation. On one hand, the solar wind delivers hydrogen to Mercury's surface, which can combine with oxygen in rocks to form water. On the other hand, the charged particles in the solar wind can sputter atoms and molecules from the surface, potentially eroding the ice deposits. But in the permanently shadowed regions, the ice is largely protected from direct solar wind bombardment, another factor in its remarkable preservation. Mercury's weak magnetic field, about 1% the strength of Earth's, creates a small magnetosphere that partially deflects the solar wind. This magnetic field is strongest at the poles, potentially providing additional protection for the polar ice deposits. The interaction between the solar wind, Mercury's magnetic field, and the polar regions creates complex patterns of particle precipitation that scientists are still working to understand. The temperature gradients around Mercury's ice deposits are among the steepest in the solar system. At the boundary between sunlit and shadowed regions, temperatures can change by more than 1,000 degrees Fahrenheit over distances of just a few meters. These extreme gradients create what scientists call thermal stress in the surrounding rocks, causing them to expand and contract, potentially fracturing and creating more rough surfaces that can trap molecules and create additional shadowed niches for ice. The stability of Mercury's ice deposits over geological time is truly remarkable. While Earth's polar ice caps have grown and shrunk dramatically over the past few million years, advancing and retreating with ice ages, Mercury's polar ice has likely remained essentially unchanged for billions of years. This stability isn't due to any active process maintaining the ice, but rather to the profound stillness of the environment, no weather to erode it, no geological activity to disturb it, no biological processes to consume it. Computer models of ice evolution on Mercury suggest that the deposits have reached a state of equilibrium, where losses to space are balanced by new deliveries. This equilibrium is dynamic at the molecular level. Individual molecules are constantly being added and lost, but static at the scale of the deposits themselves. It's like a bucket with a tiny hole in the bottom and an equally tiny trickle of water flowing in. The water level remains constant even though the actual water molecules are slowly being replaced. The presence of other volatile compounds mixed with the water ice adds another dimension to the physics of Mercury's cold traps. Molecules like ammonia, methane, and carbon dioxide have different sublimation temperatures and rates. In the coldest regions, these super-volatile compounds can accumulate, creating a kind of chemical stratigraphy where different volatiles are stable at different temperatures. This creates gradients of composition as well as temperature, with the most volatile compounds concentrated in the very coldest spots. The grain size and structure of Mercury's ice deposits remain largely unknown, but they have important implications for the physics of preservation. If the ice exists as large solid blocks, it would sublimate more slowly than if it exists as tiny crystals with high surface area. The presence of dust and other materials mixed with the ice could either accelerate sublimation by providing nucleation sites, or slow it by creating diffusion barriers. These microscopic details, impossible to observe from Earth or even from orbit, significantly affect the long-term stability of the ice. Laboratory experiments have helped scientists understand the physics of ice under Mercury-like conditions. By placing water ice in vacuum chambers and subjecting it to extreme temperature cycles and radiation bombardment, researchers can measure sublimation rates, observe structural changes, and test the protective effects of various covering materials. These experiments have confirmed that at Mercury's polar temperatures, pure water ice sublimates so slowly that it would take trillions of years to lose even a centimetre of thickness. The discovery of organic materials associated with Mercury's ice adds another layer of complexity to the physics of preservation. These organics, possibly delivered by the same comets and asteroids that brought the water, have their own sublimation temperatures and photochemical reactions. Under the intense ultraviolet radiation at Mercury's distance from the Sun, complex organics would quickly break down if exposed. But in the permanent shadows, protected from radiation and held at extreme cold, these molecules can persist indefinitely, preserved in what amounts to a natural cryogenic storage system. The physics of Mercury's ice also has implications for our understanding of volatile transport throughout the solar system. The same processes that trap water in Mercury's polar shadows might operate on asteroids, on the moons of Mars, and potentially on exoplanets throughout the universe. Understanding these processes helps us predict where volatiles might accumulate and persist, informing both scientific exploration and potential future resource utilization. As we delve deeper into the physics of stillness on Mercury, we encounter phenomena that push the boundaries of our Earth-based intuition. The concept of a billion-year-old ice deposit, unchanged except at the molecular level, challenges our perception of permanence and change. On Earth, everything flows and changes. Mountains erode, seas evaporate, continents drift. But on Mercury, in those shadowed craters, we find something approaching true stillness, a physical state so static it serves as a kind of cosmic museum, preserving samples of ancient solar system materials in nearly pristine condition. The quantum mechanical aspects of Mercury's ice preservation are particularly intriguing. At the extremely low temperatures in the polar shadows, quantum effects begin to influence molecular behavior. Zero-point energy, the quantum mechanical energy that molecules retain even at absolute zero, becomes a significant fraction of the total energy available for sublimation. Quantum tunneling, where molecules can occasionally escape even when they don't have enough classical energy to do so, might contribute a tiny but non-zero sublimation rate even in the coldest regions. The interaction between Mercury's ice and the planet's interior heat flow presents another fascinating aspect of the physics involved. Mercury still retains heat from its formation and from the decay of radioactive elements in its interior. This heat slowly flows outward through the planet's crust, including through the floors of polar craters. But the rate of heat flow is so slow, perhaps a few milliwatts per square meter, that it has essentially no effect on the ice deposits. The cold of space, accessed through the permanent shadows, overwhelms any heating from below. The role of impact gardening, the slow churning of surface materials by micrometeorite impacts, adds complexity to the preservation physics. Even in the permanently shadowed regions, tiny impacts constantly rain down, each one potentially exposing buried ice or burying exposed ice deeper. Over billions of years, this process creates a mixed layer of ice and regolith, a kind of frozen soil that has its own unique physical properties. This gardening process might actually help preserve the ice by constantly burying it beneath fresh layers of insulating regolith. As we contemplate the physics of stillness on Mercury, we're really exploring the boundaries of what preservation means in our universe. Mercury's ice represents one extreme, preservation through profound cold and isolation. It shows us that under the right conditions, even the most volatile substances can persist, for cosmic timescales. It demonstrates that the universe, despite its tendency toward disorder and dissolution, also has mechanisms for maintaining order and structure over billions of years. The stillness of Mercury's ice is not the stillness of death or absence, but the stillness of patience, of waiting, of endurance. Each molecule of ice is like a tiny time capsule, carrying information about its origin and journey, waiting in the darkness for billions of years. Some of that ice might have formed in the outer solar system before Earth existed. Some might have been created last week from solar wind hydrogen and Mercury's oxygen. All of it rests together in the permanent shadows, united in stillness, preserved by physics, waiting with infinite patience for whatever future awaits. This physics of stillness extends beyond the ice itself to encompass the entire environment of Mercury's polar regions. The shadows that never move, the temperatures that never change, the vacuum that never fills, all of these create a realm of such stability that it challenges our conception of time itself. In these regions, the future looks exactly like the past, and 1 billion years passes without perceptible change. It's as close to a stopped clock as nature provides, a place where the universe has pressed pause on the usual processes of change and decay. Now we turn to the remarkable journeys that water molecules must make to reach Mercury's polar sanctuaries, for the ice we find there didn't form in place but travelled across vast distances of space and time. Every molecule of water now frozen in Mercury's permanent shadows has its own epic story of cosmic wandering, a journey that might have begun in the outer reaches of the solar system billions of years ago, or in the nuclear furnace of a dying star billions of years before that. The primary delivery mechanism for Mercury's water is thought to be impacts from comets and asteroids, those ancient wanderers that have crisscrossed the solar system since its formation. Comets, often described as dirty snowballs, can be composed of up to 80% water ice mixed with dust and frozen gases. When one of these cosmic icebergs crashes into Mercury, it delivers its cargo of water in the most violent way imaginable, an explosion that vaporizes the comet and excavates a crater, sending water molecules flying in all directions. Picture the moment of a cometary impact on Mercury. A comet, perhaps a few kilometers across, approaches at speeds of 20 to 70 kilometers per second, fast enough to cross the continental United States in about a minute. In the final seconds before impact, Mercury's gravity accelerates it even faster. The collision releases energy equivalent to millions of nuclear weapons, creating temperatures of tens of thousands of degrees and pressures that turn solid rock into vapor. The comet itself is instantly vaporized, its water molecules dissociated into hydrogen and oxygen atoms by the extreme energy of the impact. In the aftermath of such an impact, a cloud of vaporized material expands outward from the crater. Most of it escapes Mercury's weak gravity and is lost to space. But some molecules, particularly those ejected at lower speeds or at shallow angles, fall back to Mercury's surface. As this vapor cloud expands and cools, some hydrogen and oxygen atoms recombine to form water molecules. These molecules then begin their individual journeys across Mercury's surface, bouncing and hopping in the way I described earlier, some eventually finding their way to the polar cold traps. The efficiency of this process might seem low. Most of the water delivered by a comet impact is lost to space. But over billions of years, with countless impacts, even a small retention rate can lead to significant accumulation. Scientists estimate that if Mercury retained just 0.1% of the water delivered by comets over the age of the solar system, it would be enough to account for all the ice we observe today. This inefficiency is actually encouraging. It means the source of water doesn't need to be enormous to explain Mercury's ice deposits. Asteroids provide another source of water, though they typically contain less ice than comets. Many asteroids, particularly those from the outer part of the asteroid belt, contain hydrated minerals, rocks with water molecules chemically bound in their crystal structure. When these asteroids impact Mercury, the extreme heat and pressure can release this bound water, adding to the planet's volatile inventory. Some asteroids might also contain water ice in their interiors, protected from sublimation by layers of rock and dust. But impacts aren't the only way water arrives at Mercury. The solar wind, that stream of charged particles constantly flowing from the Sun, provides a steady if modest source of hydrogen. When these hydrogen ions strike Mercury's surface, they can combine with oxygen in the rocks to form water molecules through a process called solar wind implantation. This happens atom by atom, molecule by molecule, a slow but continuous process that has been operating for billions of years. The chemistry of this solar wind interaction is fascinating. Mercury's surface rocks contain various metal oxides, compounds of oxygen with iron, magnesium, silicon, and other elements. When energetic hydrogen ions from the solar wind strike these oxides, they can reduce them, stealing the oxygen to form water while leaving behind pure metal. This process has been observed on the Moon and is thought to operate on all airless bodies exposed to the solar wind. On Mercury, with its proximity to the Sun and intense solar wind exposure, this process might be particularly effective. Laboratory experiments have shown that this solar wind implantation can create a thin layer of water molecules on rock surfaces, even at high temperatures. These molecules are loosely bound and easily mobilized when heated. During Mercury's long, hot days, these solar wind-produced water molecules would be released from equatorial and mid-latitude regions, beginning their hopping journey toward the poles. It's a kind of continuous low-level water production that supplements the more dramatic delivery by impacts. Micrometeorites provide yet another source of water to Mercury. These tiny particles, most smaller than a grain of sand, constantly rain down on all planets. Many micrometeorites are fragments of comets or hydrated asteroids, containing significant amounts of water ice or hydrated minerals. While each individual micrometeorite delivers only a tiny amount of water, their cumulative effect over billions of years is substantial. Scientists estimate that micrometeorites might deliver as much water to Mercury as larger impacts, just spread out over countless tiny events rather than concentrated in rare large impacts. The journey of water molecules from their delivery points to the polar cold traps is governed by Mercury's unique environment. With no atmosphere to speak of, molecules travel in ballistic trajectories, arcing through the vacuum above Mercury's surface. The height and distance of each hop depends on the molecule's speed when it leaves the surface, which in turn depends on the temperature of that surface. From hot equatorial regions, molecules might hop thousands of kilometers. From cooler nighttime surfaces, hops might be just a few kilometers. This molecular hopping creates what scientists call a random walk process. Each molecule follows an unpredictable path, bouncing randomly across Mercury's surface. Some molecules hop into sunlight and are destroyed by photodissociation. Others escape Mercury's gravity entirely and are lost to space. But some, by chance, hop toward the poles, where the surfaces are cooler and the hops become shorter. Eventually, if they're lucky, they hop into a permanently shadowed crater and stick to the cold surface, their journey ended. The mathematics of this random walk process predicts that it should take a water molecule released at Mercury's equator an average of about 100 to 1,000 hops to either reach a polar cold trap or be lost. Given the typical hop distance and the time between hops, this journey might take days to weeks. During this time, the molecule must survive exposure to solar radiation, avoid escaping to space, and successfully navigate the complex topography of Mercury's surface. It's a perilous journey, with a low probability of success, but given enough molecules and enough time, some inevitably complete it. The solar wind doesn't just deliver hydrogen to form water, it also creates a complex plasma environment around Mercury that can influence water transport. Mercury's magnetic field, weak as it is, creates a magnetosphere that channels solar wind particles toward the poles. This might enhance water production in polar regions, where the concentrated solar wind bombardment could more efficiently produce water from surface rocks. It's as if Mercury's magnetic field helps direct water production toward the very regions where it can be preserved. The interaction between Mercury's exosphere and its surface creates additional pathways for water formation and transport. Mercury's exosphere contains various atoms and ions, sodium, potassium, calcium, magnesium, sputtered from the surface by solar wind and micrometeorite impacts. Some of these can participate in chemical reactions that produce or destroy water molecules. For instance, oxygen atoms in the exosphere might combine with hydrogen to form water, or energetic ions might break apart existing water molecules. This creates a complex chemical environment where water is constantly being created, destroyed, and reformed. The seasonal variations in Mercury's orbit add another dimension to water delivery and transport. Mercury's orbit is the most elliptical of any planet, bringing it as close as 46 million kilometers to the Sun at perihelion and as far as 70 million kilometers at aphelion. This means the intensity of solar radiation and solar wind varies by a factor of 2 over Mercury's 88-day year. Water production from solar wind might be enhanced near perihelion, while water molecules might survive longer and travel farther near aphelion when solar radiation is weaker. The discovery of organic materials associated with Mercury's ice deposits suggests that comets delivered more than just water. Comets contain a rich mixture of organic compounds, everything from simple molecules like methane and methanol to complex hydrocarbons and possibly amino acids. When a comet impacts Mercury, these organics are delivered along with the water. In the permanently shadowed regions, both water and organics can be preserved, creating deposits that contain a sample of the comet's original composition. This co-delivery of water and organics has profound implications for our understanding of how life's building blocks are distributed throughout the solar system. The same processes that delivered water and organics to Mercury also operated on early Earth, Mars, and Venus. The impacts that created Mercury's ice deposits were part of a larger bombardment that affected all the inner planets. By studying Mercury's ice and associated organics, we're learning about the processes that might have delivered the ingredients for life to Earth. The isotopic composition of Mercury's water, if it could be measured, would provide invaluable information about its sources. Different sources of water have different ratios of deuterium to regular hydrogen. Comets from the outer solar system tend to have higher deuterium ratios than asteroids from the inner solar system. Solar wind-produced water should have a very low deuterium ratio. By measuring these isotope ratios in Mercury's ice, future missions could determine the relative contributions of different sources, essentially fingerprinting the water to trace its origins. The rate of water delivery to Mercury has likely varied over the solar system's history. During the late heavy bombardment period about 3.8 to 4.1 billion years ago, the impact rate was much higher than today. This period might have delivered the bulk of Mercury's water in a relatively short time. Since then, delivery has been more sporadic, with occasional comet impacts providing large doses of water, separated by long periods of slow accumulation from solar wind and micrometeorites. Current estimates suggest that Mercury might still be accumulating water, albeit at a very slow rate. The solar wind continues to produce water molecules from surface rocks. Micrometeorites continue their steady reign, and every few million years, a small comet or hydrated asteroid might impact Mercury, delivering a fresh batch of water to replace any that has been lost. This ongoing delivery means Mercury's ice deposits are not just ancient relics but living systems, constantly if slowly evolving. The study of water delivery to Mercury helps us understand water transport throughout the solar system. The same comets that delivered water to Mercury also visited Earth, Mars, and Venus. The same solar wind processes operate on all rocky bodies. By understanding how these processes work on Mercury, where the evidence is preserved in polar ice, we can better understand how water was delivered to all the terrestrial planets, including Earth. The journey of water to Mercury's poles represents one of nature's most improbable supply chains. Water formed in the cold outer solar system, incorporated into comets, preserved for billions of years, then delivered to the innermost planet through catastrophic impacts, vaporized and dissociated, reformed and transported molecule by molecule, finally coming to rest in the permanent shadows of polar craters. It's a journey that spans the entire solar system and the entire age of the solar system, connecting the cold depths of space to the frozen shadows on the planet closest to the Sun. As we contemplate these journeys of water, we're reminded of the interconnectedness of the solar system. Mercury's ice didn't form in isolation, but is the product of processes that operate throughout the solar system. Every molecule of ice in Mercury's polar craters is a traveller from afar, a messenger from the outer solar system or the Sun itself, carrying information about its origin in its chemical and isotopic composition. These molecules have crossed billions of kilometres and billions of years to reach their current resting places, and in studying them, we read the history of water in our cosmic neighbourhood. The delivery of water to Mercury also reminds us of the role of chance in planetary evolution. If Jupiter's orbit had been slightly different, it might have gravitationally scattered fewer comets into the inner solar system, and Mercury might have less ice. If the late heavy bombardment hadn't occurred, the delivery of water to all the terrestrial planets might have been very different. The ice we see on Mercury is the result of countless random events. Comet orbits perturbed just right, impacts at just the right locations, molecules hopping in just the right directions. Yet from this randomness emerges a pattern, accumulation of ice that follows predictable physical laws. The ongoing delivery of water to Mercury, slow as it is, means that some of the ice in Mercury's polar craters might be very young, geologically speaking. While some ice might date back billions of years, other ice might have formed from solar-wind interactions last year, or arrived with a small micrometeorite impact last month. This mixture of ancient and recent ice creates a kind of temporal collage, with molecules of vastly different ages resting side by side in the permanent darkness. As we prepare to explore Mercury's exosphere and magnetic field in our next contemplation, consider the remarkable nature of these water delivery mechanisms. They represent the universe's way of redistributing materials, of mixing and remixing the elements forged in stars. Water, that simple molecule so crucial to life as we know it, finds its way to the most unlikely places through processes that span enormous ranges of scale. From the quantum mechanical interactions of solar wind implantation to the solar system-wide orbits of comets. The story of water delivery to Mercury is still being written. Every day, solar wind hydrogen combines with Mercury's oxygen to form new water molecules. Every year, micrometeorites deliver tiny amounts of ice. Every few million years, a comet brings a major delivery. And all the while, molecules hop across Mercury's surface, some escaping, others finding sanctuary in the polar shadows. It's a dynamic system that appears static only because it operates on timescales so vast that human observation captures just a single frame of an eons-long movie. Mercury breathes, in a sense, though its breath is so thin as to be almost non-existent. The planet's exosphere, that tenuous envelope of atoms and molecules that surrounds it, is so sparse that particles rarely collide with each other, instead following ballistic trajectories that can carry them around the planet or off into space. This ghostly atmosphere, billions of times thinner than Earth's air, plays a crucial role in the story of Mercury's ice, mediating the transport of water molecules, protecting and exposing the surface to various influences, and creating a complex chemical environment where molecules are made, unmade, and remade in an endless dance of creation and destruction. The composition of Mercury's exosphere reads like a recipe for cosmic alchemy. Sodium and potassium atoms, sputtered from the surface by micrometeorite impacts and solar wind bombardment, create a faint yellow glow visible to sensitive instruments. Calcium and magnesium add their own spectral signatures. Oxygen and hydrogen, the components of water, float freely, sometimes meeting to form water molecules, sometimes drifting apart forever. Noble gases like helium and argon, delivered by the solar wind or released from radioactive decay in Mercury's interior, pass through briefly before escaping to space. This exosphere isn't stable or uniform but varies dramatically with time and location. On Mercury's day side, intense solar radiation energizes atoms, causing them to fluoresce and creating what astronomers call a sodium tail. A comet-like stream of glowing sodium atoms, extending millions of kilometers behind Mercury as it orbits the Sun. This tail, invisible to the naked eye but detectable with special filters, makes Mercury look like a comet when viewed in sodium light, a planet with a tail streaming away from the Sun. The generation of Mercury's exosphere is a violent process at the atomic scale. When a solar wind ion, travelling at hundreds of kilometers per second, strikes Mercury's surface, it can knock atoms free through a process called sputtering. These sputtered atoms are ejected with enough energy to escape Mercury's surface, but usually not enough to escape its gravity entirely. They arc through the vacuum, following parabolic trajectories that can carry them thousands of kilometers before they fall back to the surface. Micrometeorite impacts provide another source of exospheric particles, but through an even more violent process. When a microscopic grain of cosmic dust strikes Mercury at speeds of tens of kilometers per second, it creates a tiny explosion that vaporizes both the impactor and a small portion of Mercury's surface. The vapor cloud expands outward, with some atoms achieving escape velocity and others falling back to contribute to the exosphere. This process, called impact vaporization, is thought to be the primary source of calcium and magnesium in Mercury's exosphere. But the exosphere isn't just a passive product of these processes, it actively participates in the chemistry and physics of Mercury's surface environment. Atoms in the exosphere can be ionized by solar radiation, creating charged particles that respond to Mercury's magnetic field. These ions can be accelerated and driven back into the surface with enhanced energy, causing more sputtering and creating a feedback loop that enhances exosphere generation in certain regions. Mercury's magnetic field, though weak by Earth standards, plays a surprisingly important role in shaping the exosphere and potentially protecting the polar ice deposits. This field, generated by motions in Mercury's liquid iron core, creates a small magnetosphere that partially shields the planet from the solar wind. The magnetosphere is compressed on the day side, where it faces the full force of the solar wind, and stretched out on the night side, forming a magnetotail that extends far behind the planet. At Mercury's poles, the magnetic field lines converge, creating cusps where solar wind particles can more easily reach the surface. This might seem problematic for ice preservation, but the geometry of the permanently shadowed craters largely protects them from this bombardment. Meanwhile, the enhanced particle precipitation in the polar regions might actually increase water production through solar wind implantation in areas just outside the permanent shadows, potentially feeding the ice deposits with a local source of water. The interaction between the solar wind and Mercury's magnetosphere creates a complex system of electric currents and particle acceleration regions. During magnetic reconnection events, when the solar wind's magnetic field connects with Mercury's field, enormous amounts of energy can be released, accelerating particles to high energies and driving them into Mercury's surface. These events, similar to but much more frequent than the auroral substorms that create northern lights on Earth, happen regularly at Mercury, creating a dynamic and ever-changing particle environment. The sodium in Mercury's exosphere exhibits particularly interesting behavior that has helped scientists understand atmospheric dynamics on airless bodies. Sodium atoms are easily excited by sunlight, causing them to glow with a characteristic yellow light. This makes sodium an excellent tracer for exospheric processes. Observations have shown that sodium abundance varies with Mercury's true anomaly, its position in its elliptical orbit, being enhanced when Mercury is near perihelion and the solar radiation is most intense. The discovery of calcium in Mercury's exosphere was unexpected and has led to new understanding of how refractory elements, those that require high temperatures to vaporize, can become part of a planetary atmosphere. Calcium requires much more energy to remove from surface rocks than sodium or potassium, yet it's consistently present in the exosphere. This suggests that the most energetic processes, high-velocity micrometeorite impacts and the most energetic solar wind sputtering, play important roles in exosphere generation. Water molecules in Mercury's exosphere face a harsh environment. Solar ultraviolet radiation can dissociate them in seconds to minutes, breaking them apart into hydrogen and oxygen atoms. The lightweight hydrogen atoms often escape to space, while the heavier oxygen atoms might fall back to the surface or remain in the exosphere. This photodissociation is one of the main loss mechanisms for water on Mercury, constantly depleting any water that ventures out of the protected shadows into sunlight. But the exosphere also provides pathways for water formation. When hydrogen from the solar wind encounters oxygen atoms sputtered from the surface, they can combine to form OH, hydroxyl radicals or H2O molecules. This process, called recombination, happens rarely in Mercury's thin exosphere, but can contribute to the overall water budget. Some of these newly formed water molecules might find their way to the polar cold traps, adding to the ice deposits. The exosphere creates a kind of chemical reactor around Mercury, where atoms and molecules are constantly being created, destroyed, and transformed. Sodium and potassium atoms can be ionized, accelerated, and implanted into the surface, potentially creating new minerals. Oxygen atoms can combine with various elements to form oxides. Sulfur, released from Mercury's interior or delivered by comets, can form sulfur dioxide and other compounds. This chemistry, happening one reaction at a time in the near vacuum of the exosphere, slowly but continuously modifies Mercury's surface composition. The seasonal variations in Mercury's exosphere are dramatic. As Mercury moves through its elliptical orbit, the intensity of solar radiation varies by a factor of 2. This drives corresponding variations in exospheric density and composition. Near perihelion, when Mercury is closest to the Sun, enhanced solar radiation and solar wind create a denser, more active exosphere. Near aphelion, the exosphere becomes more tenuous and calm. These variations create a kind of exospheric weather, predictable but extreme. The dawn and dusk regions of Mercury, where the surface transitions from night to day or day to night, are particularly active areas for exospheric processes. As the surface heats up at dawn, adsorbed atoms and molecules are released, creating a localized enhancement in exospheric density. At dusk, the cooling surface can capture some exospheric particles, temporarily removing them from the exosphere. This creates a wave of exospheric enhancement that follows the terminator, the boundary between day and night, around the planet. Mercury's exosphere extends far beyond what we might traditionally think of as an atmosphere. The most energetic atoms can reach altitudes of thousands of kilometers, and Mercury's sodium tail extends millions of kilometers behind the planet. This means Mercury's exospheric influence extends far into space, creating a kind of extended atmosphere that interacts with the solar wind over a vast volume. Spacecraft passing through this extended exosphere can detect Mercury's atoms far from the planet itself. The study of Mercury's exosphere has implications for understanding atmospheres throughout the solar system and beyond. Many moons, asteroids, and even some exoplanets have exospheres rather than traditional atmospheres. The processes that generate and maintain Mercury's exosphere operate wherever airless bodies are exposed to stellar wind and radiation. By understanding Mercury's exosphere, we're learning about a type of atmosphere that might be common throughout the universe. The relationship between Mercury's exosphere and its polar ice deposits is complex and still not fully understood. On one hand, the exosphere provides a pathway for water molecules to travel from their sources to the polar cold traps. On the other hand, exospheric processes can destroy water molecules before they reach the poles. The balance between these competing effects helps determine how much ice accumulates over time. The noble gases in Mercury's exosphere tell their own stories. Helium-4, produced by radioactive decay of uranium and thorium in Mercury's interior, seeps out through the crust and briefly joins the exosphere before escaping to space. The rate of helium escape provides information about Mercury's interior composition and heat flow. Argon-40, produced by decay of potassium-40, similarly traces interior processes. These radioactive clocks in the exosphere connect the planet's deep interior to its outermost envelope. Messenger's observations reveal that Mercury's exosphere contains more diversity and complexity than previously imagined. The spacecraft detected not just individual atoms but also molecular species, including water group molecules, H2O, OH, and O, and possibly more complex compounds. These discoveries showed that even an exosphere as thin as Mercury's can support complex chemistry, challenging our understanding of what constitutes an atmosphere. The magnetosphere that surrounds and shapes Mercury's exosphere is itself a dynamic and fascinating system. Unlike Earth's magnetosphere, which is large and stable, Mercury's is small and highly variable. Solar wind pressure can compress Mercury's magnetosphere so much that the surface is directly exposed to solar wind bombardment at certain locations. During extreme solar events, the entire dayside magnetosphere can be compressed to the surface, allowing solar wind direct access to large areas of the planet. These magnetospheric dynamics create what scientists call space weather at Mercury. Just as Earth experiences auroras and magnetic storms, Mercury experiences its own version of space weather, though without a thick atmosphere to create visible auroras. Instead, Mercury's space weather manifests as variations in surface sputtering, changes in exospheric composition, and fluctuations in the radiation environment. This space weather might influence the long-term evolution of the polar ice deposits by affecting water production and loss rates. The discovery of Mercury's magnetosphere was itself surprising. Before Mariner 10's flyby in 1974, most scientists expected Mercury to have no magnetic field, reasoning that its small size would have allowed its core to cool and solidify long ago. The presence of a global magnetic field indicates that Mercury's core is at least partially liquid, maintaining a dynamo that generates the field. This liquid core, in turn, affects Mercury's interior heat flow, which influences volcanic and tectonic processes that might release volatiles to contribute to the exosphere. The interaction between Mercury's exosphere and magnetosphere creates phenomena unique in the solar system. For instance, sodium ions created in the exosphere can be trapped in the magnetosphere, forming a kind of sodium radiation belt around Mercury. These trapped ions eventually precipitate back to the surface, potentially creating localized enhancements in sodium concentration. This recycling of exospheric material through the magnetosphere adds another layer of complexity to Mercury's surface exosphere-magnetosphere system. The study of Mercury's exosphere and magnetosphere has required innovative observational techniques. Ground-based telescopes equipped with special filters can observe the sodium and potassium components of the exosphere, tracking their variations with Mercury's orbit and solar activity. Space-based observations from satellites like SOHO and STEREO have captured images of Mercury's sodium tail, showing how it responds to changes in solar wind pressure. These remote observations complement the detailed in-situ measurements from spacecraft missions. Future observations of Mercury's exosphere and magnetosphere promise to reveal even more complexity. Bepi Colombo carries instruments specifically designed to study the composition and dynamics of the exosphere in unprecedented detail. Its mass spectrometer will be able to detect trace species that MESSENGER couldn't measure. Its magnetometer will map the magnetic field with higher resolution, revealing small-scale structures that might influence exospheric processes. These observations will help us understand not just the current state of Mercury's exosphere, but how it has evolved over billions of years. The preservation of ice at Mercury's poles depends partly on the protection provided by the magnetosphere and the chemistry mediated by the exosphere. While the permanently shadowed craters provide the primary protection through cold and darkness, the magnetosphere helps deflect some solar wind that might otherwise erode the ice, and the exosphere provides pathways for new water to reach the deposits. It's a system where each component, surface, exosphere and magnetosphere, plays a role in maintaining the unlikely existence of ice on the planet closest to the Sun. As we contemplate Mercury's breath, this thin exosphere that barely qualifies as an atmosphere, we see another aspect of the planet's ability to surprise us. Even with an atmospheric pressure trillions of times lower than Earth's, Mercury maintains a complex and dynamic envelope of particles that influences its surface, extends far into space, and creates phenomena we're still working to understand. The exosphere might be nearly invisible, but its effects are real and significant, adding another layer to the story of how ice can exist and persist on this seemingly inhospitable world. The volatile companions that share Mercury's polar shadows with water ice tell their own stories of cosmic chemistry and delivery. These substances, including complex organic molecules, ammonia, methane, and other frozen gases, create a chemical inventory that reads like a manifest from the early solar system. Each compound has its own freezing point, its own stability conditions, its own journey to Mercury's poles. Together they form a kind of chemical stratigraphy in the permanent shadows, with the most volatile substances in the coldest spots and more stable compounds, like water ice, extending into slightly warmer regions. The organic molecules detected in association with Mercury's ice are particularly intriguing. These carbon-based compounds, possibly including long-chain hydrocarbons, amino acid precursors, and other complex molecules, are thought to be delivered primarily by comets and carbon-rich asteroids. When these objects impact Mercury, they deliver not just water, but a cocktail of organic chemistry that becomes preserved in the polar shadows. The dark material that covers much of the ice is rich in these organics, creating a carbon-rich blanket that both protects and preserves. The preservation of organic molecules on Mercury is remarkable, given the harsh radiation environment so close to the Sun. In direct sunlight at Mercury's distance, complex organics would be rapidly destroyed by ultraviolet radiation, broken down into simpler molecules or individual atoms. But in the permanent shadows, shielded from all solar radiation and held at temperatures where chemical reactions essentially stop, these molecules can persist indefinitely. Mercury's poles have become in effect a deep freeze for cosmic organic chemistry. Laboratory experiments have helped scientists understand how these organics behave under Mercury-like conditions. When complex organic molecules are exposed to the kind of cold found in Mercury's permanent shadows, they become essentially inert, their chemical bonds frozen in place. Even highly reactive molecules that would rapidly decompose at room temperature can persist for billions of years at these extreme cold temperatures. This chemical suspended animation preserves a record of the organic chemistry, delivered to the inner solar system by comets and asteroids. The presence of sulfur compounds in Mercury's polar deposits adds another dimension to the chemical complexity. Sulfur, detected by MESSENGER's instruments, might exist as frozen sulfur dioxide, hydrogen sulfide, or more complex sulfur-bearing molecules. These compounds have different volatilities than water, creating zones within the permanent shadows where different sulfur species are stable. The interaction between sulfur compounds and water ice might create unique minerals or chemical complexes that exist nowhere else in the solar system. Ammonia, if present in Mercury's polar deposits as some observations suggest, would be particularly significant. Ammonia has a lower freezing point than water and could act as an antifreeze, potentially creating layers within the ice deposits, where ammonia-water mixtures remain mobile at temperatures where pure water ice would be completely solid. This could create a kind of chemical gradient within the deposits, with pure water ice in some areas and ammonia-rich ice in others, each with different physical and chemical properties. The carbon dioxide that might be mixed with Mercury's water ice tells us about the delivery of volatiles from different sources. Comets typically contain significant amounts of CO2, sometimes called dry ice when frozen. On Mercury, CO2 ice would be stable only in the very coldest parts of the permanent shadows, sublimating rapidly if temperatures rise even slightly. The distribution of CO2 relative to water ice could help scientists understand the temperature history of the polar deposits and the relative contributions of different types of impactors. Methane and other light hydrocarbons potentially present in Mercury's polar shadows represent some of the most volatile substances that can be preserved there. These molecules, which would be gases at Earth temperatures, require the extreme cold of Mercury's permanent shadows to remain frozen. Their presence would indicate that Mercury's cold traps are efficient enough to capture and retain even the most volatile substances delivered by impacts, making them incredibly effective preservation environments. The interaction between these various volatile compounds creates a complex chemical environment, even in the extreme cold of the permanent shadows. Different molecules can form clathrates, cage-like structures, where one type of molecule traps another. Water ice can form clathrate structures that trap methane, carbon dioxide, or other gases, creating compounds that are more stable than either component alone. These clathrates might help explain how extremely volatile substances can be preserved in Mercury's polar deposits even when temperatures fluctuate slightly. The isotopic composition of these volatile companions provides clues about their origins. Different sources of volatiles have characteristic isotopic signatures, the ratio of heavy-to-light isotopes of elements like carbon, nitrogen, and sulfur. Comets from the outer solar system typically have different isotopic ratios than asteroids from the inner solar system. By measuring these isotopic signatures in Mercury's polar deposits, future missions could determine where these volatiles originated and how they were delivered to Mercury. The layering of different volatiles in Mercury's polar deposits creates what scientists call a volatility gradient. In the warmest parts of the permanent shadows, only water ice and the most stable compounds can persist. As temperatures drop toward the coldest regions, progressively more volatile substances become stable. This creates a kind of chemical zoning, with different areas of the polar deposits having different compositions based on their temperature. This zoning provides information about the temperature distribution within, the permanent shadows, and how it has changed over time. The organic molecules in Mercury's polar deposits might preserve information about prebiotic chemistry in the early solar system. Some of the complex organics delivered by comets and asteroids are thought to be precursors to biological molecules, the building blocks from which life might arise under the right conditions. While Mercury itself is far too hostile for life, its polar deposits might contain a frozen library of the chemical ingredients that, when delivered to Earth, contributed to the origin of life. The discovery of these volatile companions has changed our understanding of what Mercury's polar deposits represent. They're not just ice deposits, but complex, multi-component volatile reservoirs that sample the chemistry of the objects that have impacted Mercury over billions of years. Each impact delivered its own mixture of volatiles, and the polar cold traps have preserved these contributions like a chemical archive, sorted by volatility and protected by shadow and cold. The interaction between solar wind and these volatile deposits adds another layer of complexity. When solar wind particles do reach the deposits, either through magnetic field cusps or by scattered trajectories, they can trigger chemical reactions even at extremely cold temperatures. cosmic rays, which can penetrate the permanent shadows, might also drive slow chemical changes, creating new molecules from the raw materials present in the deposits. Over billions of years, these processes might have created unique chemical compounds that exist nowhere else. The seasonal variations in volatile stability, driven by Mercury's elliptical orbit, might create a kind of volatile pumping in the polar regions. As Mercury approaches perihelion and temperatures rise slightly even in the permanent shadows, the most volatile substances might sublimate from warmer areas and recondense in colder spots. This could create a slow migration of volatiles toward the coldest regions, concentrating the most temperature-sensitive compounds in the deepest, darkest parts of the polar craters. The role of these volatile companions in the overall stability of Mercury's polar deposits is still being investigated. Some volatiles might act as stabilizing agents, helping to preserve water ice by creating protective layers or chemical complexes. Others might destabilize the deposits by lowering melting points, or creating chemical reactions that release gases. Understanding these interactions is crucial for predicting the long-term evolution of the polar deposits and their response to changing conditions. Future missions to Mercury will need sophisticated instruments to fully characterize these volatile companions. Mass spectrometers that can identify specific molecules, infrared spectrometers that can detect different ices, and drilling systems that can sample different depths within the deposits will all be necessary. The technical challenges of operating such instruments in Mercury's extreme environment, particularly in the permanent shadows where solar power isn't available, will require innovative solutions. The study of Mercury's volatile companions has implications beyond Mercury itself. Similar mixed volatile deposits probably exist on the Moon, on asteroids, and on other airless bodies throughout the solar system. The processes that create and preserve these deposits on Mercury operate elsewhere, making Mercury a natural laboratory for understanding volatile chemistry in space. What we learn from Mercury's polar deposits will inform our understanding of volatiles throughout the solar system and potentially throughout the universe. As we near the end of this contemplation of Mercury's exosphere, magnetosphere, and volatile companions, we see how these elements work together to create and maintain the unlikely existence of ice on the planet closest to the Sun. The exosphere mediates the transport of volatiles, the magnetosphere provides partial protection from the solar wind, and the various volatile compounds create a complex chemical environment that has evolved over billions of years. Each component influences the others, creating a system that is more than the sum of its parts.